Okay, sir, we are live now. Please start
Okay,
the
very
session.
good. Thank you. Good morning, good afternoon, and good evening, everybody. Mr. Malti Teal, Professor Somi, and all the authors who have joined this workshop and the participants. It's my proud privilege to welcome you all to this workshop. And let me share a little bit background with you. We have had very successful 3 days symposium, and today also we are having 7 parallel workshops. So, and this is the workshop on sediment management in reservoirs for sustainable development. And the interest in this workshop is maximum because we have 12 papers to be presented, and it goes till 4 in the evening as per the Indian time. I'll not take much of time, but I'll just want to add here that segmentation, well, I was a young engineer about 40 years back. It was being considered that it is a typical problem of Indian subcontinent. And others were working at it, but they were thinking that it is not that severe problem. But now it's everybody has so become so serious that it's a global problem, and we have this in Icold Committee J, which is headed by Mr. Malti Teal, and that also Malti Teal is the chair for this committee in Icold, and this committee has also done a wonderful job when coming to the segmentation. I would like to add here that in view of the climate change, we all of us need to work somehow on the reduction of the process and the control or mitigation of the sedimentation process, because in times to come, the number of sites for fresh new sites for the storage have reduced, and it is because of the population pressure in most of the countries, it is becoming difficult to construct new dams. So the existing dams where we have storage uh, are very important, and those are the dams where we can sustain or we can do something towards climate change. Because climate change phenomena is becoming is happening. Earlier, it was being told that climate change is likely to happen, but now it is happening. All of us are feeling about it. Extreme events are there. In India, we are getting affected by extreme events to a larger extent because we already have had floods and droughts because of this climate change, and unpredictable extreme events are there. So I'll not take much of time. And this workshop is one of the, I think, most important workshops for us here in India. And also, I understand for globally also, it is very important. So with that, I'll hand over to Mr. Marty to please go ahead with the review of the importance of sediment management for ensuring the sustainability of reservoir and runoff river projects. Mr. Marty Teal, please.
Thank you, Mr. Sharma. I appreciate it, and I'm happy to be here. I'm going to share my screen, which I hope you are able to see the presentation. Okay. So thank you for having me and inviting me. I know there's a great deal of interest in this subject worldwide, but especially in India, as we saw by some successful workshops that we had there already at the end of 2019 in New Delhi and Chandigarh. I'm just going to give a brief introduction for the workshop before we launch into the papers. Again, my name is Marty Teal. I work for West Consultants in San Diego, United States, and I currently chair Technical Committee on Sedimentation of Reservoirs of Icold. So this workshop is for sediment management in reservoirs for sustainable development. There's a number of quality papers that will be presented after this introduction. Some of the major topic areas are listed here in terms of best practices, sediment flushing, improving efficiencies, replenishment downstream and passing sediment, including turbidity currents and sediment bypass tunnels. Of course, the effects of climate change, and then management and cascade reservoirs. So those are some of the major topics. The presenters that you will see, I think, are very high quality here. I wanted to give just a brief background, kind of set the tone for the rest of the session and talk about sustainable sediment management in reservoirs. So I'll give you a brief overview, talk very briefly about sediment management and the methods, because our other presenters will be talking more in detail about that. A few words about what I believe to be sustainable development, how climate change impacts sustainable development, and then a few takeaways at the very end. So for most of us, at least I know in my career and in this country, we're dealing mainly with existing dams where perhaps those dams were not designed in a sustainable manner, or they use kind of the old concept of a design life with dead storage. And once that is full, there's really no sustainable way of managing. So we're trying to do a retroactive measures to extend the life of the project. If you're fortunate enough to be involved in the planning and working with new dams, hopefully you're able to implement some of these measures in the planning so that it can become a sustainable project, and the sediment will not really take away the benefits, as I'll show later on in this presentation. So first of all,
Marty,
yes.
Sorry to interrupt you. You are now showing the like a note mode. Please change the presentation mode. Yeah, display
For
setting.
letting me know.
Yes, second one.
That better
Yes.
now?
Yeah, good,
Okay.
good. Thank you.
Thank you. So when we look at creating a project, of course, it's a big investment to create any dam. And we have to ask ourselves, why are we creating that dam in the first place? And the figure on the bottom is supposed to be not an ice cube, but a volume of water. So we're creating this dam, we're spending a lot of money to create storage. We're also creating head, but for many, the main reason is to create storage so that we have water for water supply, irrigation, of course, produce food production, flood risk reduction, which is very important. And then, of course, hydropower generation, you need to consider both the volume and the head. So when we start planning for a project, as I mentioned previously, a lot of times I think in the past, there really wasn't much thought for what happens after the dam reaches its design life. So if we're going to think more sustainably, we have to think, how are we going to protect our investment, all that money that we're putting in up front? That is, how do we make our project sustainable? And also, how do we make it resilient? So I'll talk more about both those concepts. Of course, when we get into planning the dam, especially if you're in an arid area, and I live in an arid area in the Western United States, we have many periods of drought as well as floods. And so in order to have enough water to have irrigation, provide water supply, and everything else that provides benefits, we need to make sure that we have enough carryover storage during the dry years to provide that water. And so within our planning, we can figure out what kind of volume that we need. The example I have here is the Colorado River, which has many ups and downs. And so we need to make sure that we have sufficient volume so we have reliable supply over what have tended to be multi-year droughts in the past, which apparently will intensify into the future. Another major issue, of course, is storage loss due to sedimentation. And this is just one example from the United States, but in the areas that are more arid in the Western United States and mountainous, you can see that we can have up to about 2% loss of sediment per year. and within our reservoirs. And so that is significant, because it doesn't take that long to start losing significant amounts of storage. When we look at the amount of storage that's been built, and this is within the United States, and I have to thank Dr. Annandale for providing these slides for me to use. If we look at the top curve, the blue curve, that basically demonstrates the amount of storage that we would have if we build no new dams in the country. That is, it basically levels off in the after year 2000. But what is happening because of that loss of storage due to sedimentation, we're actually seeing the other three curves, the brown, yellow, and red curves, which display different scenarios for sediment loss. The brown curve would be a low storage capacity loss, while the red curve would be high loss rates. And so there's a range in there, but you can see that we're losing storage. Looking at this same thing another way, if we take into account population change and we look at the amount of storage per capita, we can see that in the future, even if we don't construct any new dams, we'd still be, and we don't have any sediment loss, any loss of storage due to sedimentation, we're still seeing a reduction in the amount of storage per capita that we have. And then of course, with sedimentation losses, we would have even lower amounts of storage. So, looking at that range of results, if I pick a medium result, so a medium loss of storage due to sedimentation, and I see where we are now in about 2020, if I look at a per capita basis, that actually, on a per capita storage basis, we're about where we were in 1950 in terms of storage per capita. And we know that with climate change and change in variation in our hydrology, which I'll talk about in just a moment, that's really not a good place to be. So in terms of the management of sediment, the way that we can manage it would be to either minimize the sediment that's actually getting into the reservoir, or maximize the sediment transport either through or around the reservoir. Trying to maintain a seasonal distribution of sediment transport can lead to sustainable measures and also be good for the environment. And then maintaining natural distribution of transported sediment, and getting back to the strategies for controlling sediment. At least in this country, the way that dams used to be designed was that we would provide enough, in quotes, storage volume for whatever the design life was. 100 years was often a number that was used. So you would estimate the amount of sediment that would come into your reservoir over 100 years. You would provide dead storage for that, and nobody thought after 100 years what would happen. Of course, if we want to have a sustainable project, we have to build in management strategies as part of the planning process with the dam so that they become sustainable. The management strategies, three broad categories: yield reduction upstream of the reservoir, routing through or around the reservoir, or sediment removal after it's already settled, which tends to be some of the most costly measures. And again, others will talk about some of these strategies in more detail. I wanted to just give the overview here. This is a figure courtesy of Dr. Sumi and Dr. Kantush that exemplifies these strategies. First of all, the sediment yield reduction, reducing the amount of sediment that is able to get into the reservoir, either check dams, salvo dams, forestation projects, or if you're able to route sediment either with bypass tunnels or density current venting, that will keep the sediment moving so it does not able to settle within the reservoir. Or finally, sediment removal, which again tends to be very costly, excavating, dredging, resulting trucking, things like that, which tends to cost a lot of money. In terms of which strategies might be most applicable to a particular project, there's different ways to look at it. This is one that Dr. Sumi and George Annandale, Dr. Basson, and others have worked on, looking at sustainability and no sustainable projects, and what measures have been successful for managing sediment in those projects. Yeah, I'm not going to go into depth here, but that is available in other references. So what is sustainable development? A lot of people, and myself included, like the definition from the Brundtland report, which says that sustainable development seeks to meet the needs and aspirations without compromising the needs of the future to meet those. And so if we're going to have sustainability, we need to make sure that our children and grandchildren are able to enjoy the same benefits that we're able to enjoy today. So if we don't manage sediment, the projects will not be sustainable. We're going to lose those benefits. And the old design life concept will not provide the benefits that we enjoy today with the investment in the dam. This is one example. This is Matilaha Dam, which is actually only a few hours from where I live. This is completely silted in. You can see some activists went and actually painted a picture of the scissors to remove the dam. But they're considering different measures to decommission this dam, which would cost hundreds of millions of dollars when you take all the different factors into account. So it's very expensive. So along with sustainability, I have that same quote that I've highlighted, the word future. That is, we're trying to meet the needs of the present without compromising the ability of the future generations to meet those needs. So when we look at the future, when we look at potential climate change, we're looking at meteorologic change, changes in the amount of precipitation, the form that it takes, say rain instead of snow, and an increase in variability. And then, of course, that meteorologic change translates into hydrologic change, where we see changes in both the mean flow and increased variability in those flows. And those, of course, will also impact the sediment loading that we will get within our project. And a number of studies have been done in terms of how precipitation and hydrology will change in the future. This is from the IPCC from 2013, where they looked at two different scenarios for low emissions and high emissions, and some different results from different models. The stippling with the dots and the dashes indicate ranges of variability. You can see that there's many areas of the world where the change in predicted precipitation is greater than 30 up to 50%. So, and that's just average precipitation. This doesn't say anything really about the variability. You know, looking at the Indian subcontinent, here's some more results, and this is from global climate change models. And this shows the 10th and 90th percentiles as well as the median. And a predicted percent change, the top row is change due to predicted rainfall, and the bottom is temperature. But you can see that you know, the predictions are showing that there will be extreme changes. Okay, this is a result looking at runoff volumes in the middle of the 21st century compared to a historical period, the baseline of 1900 and 1970. This is from a paper by Milley, but it's also based on IPCC. And basically the areas where their color indicates that this is the aggregate results from 12 different models. If at least eight of the 12 models were in agreement, then those areas are colored in terms of what the predictions were between the 12 models. The areas with no color indicates that there was not agreement by at least 8 of those models. But again, you can see that the changes in annual runoff volume are predicted to be fairly severe. And I talked about increased variability. Again, looking at those scenarios and from the IPCC report and looking at some different phenomena, they had predictions for both the early 21st century and the late 21st century. And I'll focus on the later period, but basically they're saying that warmer days or fewer cold days and nights is almost virtually certain looking into the late 21st century. Heavy precipitation events is very likely over most of the mid-latitude land masses, and increases in intensity or duration of drought is also likely on a regional to global scale. So we're seeing that they're predicting an increase both in heavy precipitation and drought. So we're seeing increased variability, okay, and that's going to have an impact both on the hydrology and the sedimentation in our projects. So if we're going to have sustainable projects, we have to account for changes in hydrology, both in terms of how we meet the demands that we have, the capacity that we need for storage, and then also in terms of safety of our dams, of being able to pass certain flood events. And for sustainability, we have to take into account changes in sedimentation that will go along with those climate changes, so which could affect the amount of sediment that we get, the gradations. Perhaps we might get coarser rather than finer gradations, and the strategies that we might need to maintain the capacity in our operations. So if we look at we want a reliable project, if we set reliability at a certain level, in this case, example here, it's 99%. We can see that in this curve, this is example, the red curve is showing a larger storage project. The dashed blue line is a medium storage project, and the black line is a smaller storage project. And on the bottom axis here, the x-axis is a coefficient of variation. And so with the larger storage project, as we get more variation, the percent of the yield that we're able to meet goes down, but not that much. The smaller storage projects are much more sensitive to an increase in the variability of flows. With climate change and the increase in variation that I was just talking about, you can see that for a large reservoir, we have a decrease in the amount of yield that we can expect. When we take into account, however, effects of sedimentation, that basically changes us from the large reservoir curve to a smaller reservoir curve because of the volume that's taken up with sedimentation. So in that case, we might only be able to provide, say, 60% of the yield compared to 90%, 90+% if we had a larger reservoir. So this is just one example of the kinds of changes that we can expect with the impacts of both sedimentation and climate change. So I'm going to wrap up here and let's talk about very briefly a life cycle management approach where hopefully we can take into account some of these ideas about sediment management and sustainability in the planning of design. You're always going to have operation and maintenance costs, and hopefully sediment removal will not be necessary, at least by mechanical means, that we're able to use some of the sediment management measures that I mentioned very briefly and others will talk about in the session to ensure that we maintain the benefits of our projects and the sustainability. So the end here, I want to stress resilience against climate change. It helps if we can have larger reservoir storage spaces, and we need to ensure the benefits that I mentioned: water supply, irrigation, flood management, and hydropower. We're only going to keep those larger reservoirs if we can prevent loss of storage due to sedimentation. And for sustainable development, to create and maintain that intergenerational equity, adopting the life cycle management approach, we need to manage the reservoir sedimentation, again, to maintain the amount of storage that we've invested this money in. So with that, these are just two pictures of the Matilaha Reservoir again, showing the sedimentation. So I will end my presentation here. Thank you.
Thank you, Mr. Maltiti. It was a wonderful presentation, and I think it was the right thing that for the entire day you have set the tone. So, and I understand it's midnight for you, so it's very late. And your second presentation, I'll request the host to please play it, the recorded presentation. Host, are you listening? Virtual host?
Yes, sir, I'm listening. Please tell me.
Yeah, please. Thank you so much.
Shall I play second video?
Yes, please start that.
Afternoon. My name is Martin Teal. Today I'll be speaking on predicted sediment transport for pool lowering at Noachaki Dam. My co-authors on this paper are Filippo Bresson from West Consultants and Kurt Jowdy from the Tennessee Valley Authority. In terms of what I want to talk about today, first of all, I'll give a little bit of information about the background and purpose of the study, the approach that we took to complete the study, which included modeling, the model development that we went through to produce the set of model results from which we drew conclusions, and then I'll end up with a few notes on the status of the program. So in terms of background and the purpose, Noachaki Dam is in the eastern United States. It's in the state of Tennessee. It is a dam owned by the Tennessee Valley Authority. It's near the town of Greenville, Tennessee, and it drains to the Tennessee River at Knoxville, which you can see in the figure. The dam was built in 1913, so it's an older structure. It has an OG spillway and it has one vertical gate. You can see in the picture below that the dam has a powerhouse which is now not producing any energy. It has a portion which is a non-overflow section on the right abutment. It has the fixed gate, which is the vertical lift gate. And then most of the dam is the spillway section, which you can see in this picture is actually spilling flow. As I mentioned, the powerhouse was decommissioned, so it's no longer producing electricity. The reservoir is mostly filled in with sediment, and also the gate is permanently closed. So that basically forces all flow over the spillway at this point. So for this project, in order to perform periodic dam inspections for dam safety, the Tennessee Valley Authority needed to basically stop the overflow of the dam so they could get in, do maintenance on the gate, and do inspections. However, to do that, they needed to release the old fixed gate. And when they did that, they expected that some sediment that had been deposited in the pool would be released downstream. And so some of the questions that they had were, would they need to dredge upstream sediments in order to avoid high releases? Or if they didn't dredge, what kind of releases would they have? What would the concentrations be? And this information would inform environmental impact assessment report, which they're required to complete before doing any work. That would include any potential impact on fishes or aquatic species downstream. And so what they wanted to do was this modeling study to help them predict what would happen if they went ahead and removed this gate. So they contracted West Consultants, and we did the modeling work for them. The approach that we took to do the sediment transport modeling was to set up a two-dimensional model to examine both potential mobilization of sediments and concentrations of sediments when the gate was removed. So we wanted to know what would the maximum concentration be that was released, how long would it last, because that would also have an impact potentially on species downstream. How do those predicted concentrations, or how would the predicted concentrations compare to naturally occurring concentrations that you would get, say, during normal storm events? And also, would there be a way for the authority to avoid having to dredge, which would be quite costly, and also incur some additional studies that would need to be done? So those were some of the main questions that we hope to answer with our modeling study. So here's again another picture of the dam, this one looking straight upstream. You can appreciate that pointer here. that the pool is mostly filled in. You can see the bar deposit. This would be on the right side looking downstream. There's an island up here. These are very shallow areas. Again, this dam has been filling in with sediment for many years. So the idea is that in order to perform maintenance on the dam, they would have to remove this gate. But when they remove this gate, how much sediment would be mobilized here and what kind of concentrations would they be getting downstream? So that's what we hope to answer. Continuing on with the approach, we decided that we would use a two-dimensional model that was developed by the United States Bureau of Reclamation, which is the SRH 2D model. It uses depth average St. Bernard equations, 2D depth average St. Bernard equations, I should say. It has coupled non-equilibrium sediment transport, which we felt was appropriate for modeling potential movement of sediment within the reservoir and downstream as well. So what's shown on this slide is actually the cover of the user's manual. This is freely available software, by the way, produced by the US government. So developing the model, we first, of course, needed some bathymetry of the lake. This picture here shows that bathymetry superimposed on a Google Earth photograph, where you can see that it's a fairly shallow reservoir. There are some deeper sections very close to the dam, but a lot of it is pretty much silted in. So in order to model this, we came up with two different computational meshes, which are shown here. First of all is the mesh with the gate closed. So before they would remove the gate, to see what kind of sediment concentrations might occur under natural storm conditions that would pass over the dam. And then secondly would be the grid on the right side, which is with the gate open. You can see the notch that would occur there when the gate is opened up. And so basically starting the model simulation with an open gate, but the pool at, and the bed, I should say, of the reservoir at existing conditions would allow us to see how much would scour for different flow rates and what the resulting concentrations might be released from the dam. So in order to perform the modeling, we needed some information about sediment materials on the bed and banks. We had programmed a campaign of sediment sampling, to collect some data. We proposed the locations, and the TVA personnel went out and did the sampling. Unfortunately, because of safety reasons, they could not get too close to the dam. So some of the locations that we had initially marked for samples, they were not able to collect. But we did get a good range of representative samples of sediment that was available both in the bed and on the banks. The lower part of the reservoir, which is where we would expect sediment to be mobilized. So we took that information and we were able to input different sediment layers within the two-dimensional model. That's actually one nice thing about the SRH2D model, is where you can specify different sediment layers, and it will treat each one of those separately as it erodes. So we need to characterize the layers. And based on the samples that we had, you can appreciate in this diagram, we of course defined the dam as non-erodible. But then we had different areas of the reservoir, which were either mainly sand, mainly silt, and some were the beds and some were the banks. And so we specified those different material types separately within the reservoir and within the model. So when it did the calculations for erosion, it would be able to look at the different sediment types present in different parts of the reservoir. So we looked at a couple different flow cases. The first one were low flows, because they were planning on going out and doing this work during low flows if possible. So that corresponded to about 1,900 cubic feet per second, or 54 cubic meters per second. We also wanted to look at a minor but kind of normal flood event. And so a normal yearly peak runoff would be about 13,000 cubic feet per second, or about 371 cubic meters per second. So we wanted to run both of those different flow events. In terms of our boundary conditions downstream, we had rating curves on the river that TVA was able to provide us. We prepared a surface model in order to characterize the hydraulic roughness of the materials of both the bed and the banks. We estimated the Manning's coefficients based on guidance from Chow, sediment grain size distributions. We use a total load formula of Englund and Hansen within the model. And the erodibility properties of the fine sediment were based on work by Jean-Louis Briot, who's a professor at Texas A&M University. And we found that the fine graded sediment were within the high and low plasticity silt range. And so we use that information within the model as well in terms of how easily eroded the sediment would be. The subsurface models I mentioned, we use to characterize the different sediment types at different sediment layers at different elevations, such as non-cohesive materials as sand or cohesive materials such as silt and clay. So moving on now to the model results. We were able to run 4 different cases successfully. The first one was with the gate closed, so that first geometry that I showed with the gate closed and a low flow going over the top, which would simulate existing conditions with a constant upstream flow, kind of normal low flows, which corresponded kind of as a background when they hope to go in and do the work on the dam. The second case we looked at was the closed gate, but with the yearly event, about 13,000 CFS flow. The third case that we looked at was with the gate open and using the bathymetry that was surveyed. And so this would correspond to what would happen if they went in during low flows and they pulled out the gate, and what would be expected to erode. Now, one of the things that we came across with the survey, as I'll show in just a minute, is that when they did it, there was a scour hole. When I say scour hole, but there was a deeper portion, we think, in front of the dam. The way the reason that I say I think is because, again, there were some limitations as to how close they could get to the dam for safety reasons. So we were not as confident in the accuracy of the bathymetry data very close to the dam. So what we did as kind of a worst case is we created a second geometry of the pool, which we called flat bathymetry. That is, we took the elevations of the sediment a distance away from the face of the dam, and we assumed that there was a flat bed all the way from that point to the face of the dam. This would be more conservative in terms of potential sediment releases, and it was a sensitivity to see how much sediment we would predict to be released or what kind of concentrations we would have with the 2 different types of bathymetry in the pool. So in terms of the results, before I present the results, I will show you this picture where we created a Thalweg line, or the line at the lowest points based on bathymetry, because we were looking at results along that line, not necessarily straight up the river, but the line kind of following the flow path towards that gate opening. And so that's where we're looking at scour results along that line. So looking at the results, we can see that with the cases with the gate closed, we're showing water surface elevations here. So of course you have a higher water surface elevation with the yearly flow of 13,000 CFS compared to the low flow of 1900 CFS. But those of course are both forced over the spillway. When we open the gate, you can see that the water surface elevations drop, but there really wasn't that much difference between the cases with the surveyed bathymetry, which again had that deeper portion very close to the dam, or the flat bathymetry. And I should go back just a sec, and you can see in this plot here that the deeper portion in front of the dam is shown in the green and blue colors. And so for the flat bathymetry case, we basically took the elevations shown in the orange colors and extended those all the way up to the face of the dam. You can also see on this plot that deeper portion very close to the face of the dam within about the first 30 meters or so. So that was water surface. When we looked at shear stresses that we had here, you can see that, of course, with the closed gates, the shear stresses were not that high. But when we had the gates open, especially in the first part of the simulation, we had erosion going on, as we expected it would. And based on those higher shear stresses, those were closer to the dam. And so the results that we're showing here really verify that we're seeing the higher shear stresses. What I'm going to do now, and this is showing distances past 100 meters away from the dam, I'm going to zoom in a little bit. And so now we're looking at the area within the first 100 meters or so from the dam. And so we can see that, of course, the shear stresses are much higher very close to the dam, and then they drop off fairly rapidly. We do see that for the case with the closed gate and 13,000 CFS, we do have a slight increase as the reservoir shallows a little bit further away from the dam, again, within that first 60 meters or so. But the shear stresses were not highly erodible, but they were enough to be expected to erode the fine sediments that we had. In terms of concentrations, when we looked at the simulations with the closed gate and the low flows, or the the open gate with the low flows, the predicted releases of sediment in terms of concentration were very low, less than 20 milligrams per liter. When we had the situation with the closed gate and the higher flow, we did get much higher sediment concentrations through there. Okay, and there's a plot showing a concentration with time, and this is the case with the open gate with the surveyed bathymetry. And so, as we might expect, at the beginning of the simulation, the concentration goes up very quickly as it erodes and tries to find a new equilibrium. But over time, especially after about 10 or 20 hours, it gets to an equilibrium condition, and the concentrations drop off very quickly. So the maximum concentration that we saw was just over 100 milligrams per liter, but it did not last very long, only a matter of a few hours. So the sediment concentration during the flood of 13,000 cubic feet per second, so the yearly flow, was around 600 milligrams per liter. And that's with the closed gate. So that tells me that for a natural event with the gate in a closed position, the concentration of sediments going downstream is much higher than the case with the gate removed and the low flow, which is under the conditions under which they would be replacing the gate. So that shows us that the expected releases in terms of concentration would be much smaller than the river currently experienced under natural conditions. In terms of predicted scour depths that we had, the measured bathymetry, using the measured bathymetry, excuse me, the maximum scour we predicted was about 60 centimeters, so not very much. And the volume was very small, about 8.5 cubic meters. As I mentioned, the maximum concentration, like we saw on the last slide, was just over 100 milligrams per liter. And the plot on the bottom shows the development of scour with time. So you can see that it was very gradual. It was also located the gate is right here. So right in front of the gate is where we saw the maximum amount of scour, but it really, after about 20 hours or so, it was very slow to develop. So depending on how long they would take or leave the gate out, they would expect, or we told them that they might expect scour up to about 60 centimeters, so not that much. So the results expressed both in feet and meters here. So for the measure bathymetry, we saw that where there's already that low point just in front of the dam, the maximum predicted scour was on the order of 2 feet or 60 centimeters, with the maximum concentration of about 100 milligrams per liter. When we ran the case with the flat bathymetry to account for potential inaccuracies of the survey data immediately in front of the dam, of course, we did see more scour. That was on the order of 6.5 feet or about 2 meters. The concentration did not increase a lot, though. It was on the order of 160 milligrams per liter. And again, comparing both of those to a natural high flow or a yearly high flow event with the gate closed and flow going over the spillway, the concentrations for that case were about 600. So whether we used a measured or flat bathymetry, we were predicting that the concentrations would be much lower than the river would see normally on an annual basis due to natural flooding. So to arrive at my conclusions, the sediment transport modeling that we did showed that the gate would probably result in fairly localized scour for a fairly brief period. There would be a temporary increase in concentration, but again, those concentrations would still be much less than the river experienced during normal yearly flood events. The transport of sediment through the open gate was expected to be minimal. Therefore, we told TVA that dredging would not be required. That was good news for them because that meant that they could avoid additional environmental studies, additional permitting, and additional costs that go along with all that. So that was a good outcome for them. And just a quick update on the status. We originally completed this work back in 2018. They had to file the environmental assessment, which basically the recommendation was findings of no significant impact. That was approved. And so they were actually able to go in and pull the gate, do the inspection, and do the gate replacement in the middle of 2019. So it was a very successful study. The modeling was very interesting, and we were very pleased with the results, as was our client TVA. With that, I would be happy to take any questions that you might have.
Hello? Can I ask something? Sumi? Marty?
Yeah.
Professor Sumi, please go ahead.
Okay. Thank you very much. Interesting presentation. My question is, this new gate or gate opening is objectives is like conduct inspection upstream, right?
Yeah, they had to, because the gate is normally closed, all the flow would go over the spillway.
Yes.
It's uncontrolled spillway. So in order to inspect that part of the spillway, they had to open the gate to send the flow to the other side. And so, but they were worried because it was already so filled in with sediment that when they opened the gate, they were going to release a lot of sediment and with a lot of environmental impacts. And so they had to show the regulators that there would not be serious impacts when they opened the gate. And so that we were able to show that with the modeling.
I see. So next question is, this opening is open spillway gate is not directly sediment management objectives.
That's correct. That's correct, because this is a project that was built, I had in the first slide, I think in the 20s maybe, And even when the TVA was formed, they inherited this project, and it was already filled in with sediment. And so they took out all the generating equipment. It no longer generates hydropower. It's full of sediment. But they're still responsible for it and the safety of the dam, and so they have to inspect it. And this wasn't necessarily a sediment management, because they've decided their solution is to leave it full. But because it is full of sediment and they have to manage it and they had to inspect it, this was showing the study that we did on sediment movement in the reservoir for those objectives.
Okay, thank you very much.
Any more questions, please? So we move to the next paper by Professor Sumi, Sediment Management in Cascade Reservoirs. Professor Sumi, please.
Okay. Okay. So thank you very much for a good workshop on the reservoir sedimentation management. It's my pleasure to have a presentation on this title. I'm Tetsuya Sumi from Kyoto University. So today's my topics is how to consider the sediment management. The material is already explained as an introduction. My important point is how to integrate it management in sediment catchment basin scale objectives. And today is my focusing of usually in the basin scale, we have many dams as a cascade manner, series of dams. How to consider the upstream dams and downstream dams, how to have a good linkage with sediment management. It's a main topic. So I'd like to show some examples in European cases in Rhone River, Swiss, France, a good example in the Rhone River example. And later on, I would like to discuss about the 3 Japanese cases, Kurobe River, Mimi River, and Yahagi River, and the conclusion and recommendation. So integrated management concept is like this. So from upstream mountain sediment yield production area and downstream river channel and river mouth and the coastal area. This like a system is connected. But usually we have storage dams, and sometimes it's erosion control work in mountain area. And this work is of course important for disaster management and or water storage. But sedimentation is like maybe long-term impact to the downstream. And sometimes is riverbed degradation or riverbed change. Okay. Sorry. Okay. So important point is how to connect it to sediment like a routing system from upstream to the downstream. And finally, those sediments go to the coastal area. So our direction is how to balancing of sediment transport from source of the river to the coast. And to do that, we need some like a monitoring to assess the current bed load and suspended load, wash load. And if we have any suitable actions, how will change in the future? So already Marty explained some several methodology. We already provided some schematic view. So if we focusing the sediment routing techniques, routing means how to pass through the sediment through the reservoir. Our approach is already focusing the sediment bypass system with Swiss and Taiwan. We have periodically conducted international workshops, sediment bypass tunnels. But in case of bypassing is we have two methodology, fully bypassing from the upstream to the downstream, or some like a middle area to take a sediment to the downstream with some partial drawdown like this. This partial drawdown is we have a chance to shorten the tunnels length, but the drawdown operation needed. And sediment sluicing or flushing is of course like a drawdown and increasing the velocity and pass through the sediment through the bottom outlet or some deep spillway gates. And density current venting also like conducted in China, Taiwan, other countries, and a large reservoir. It is very difficult to completely draw down or passing through. So bottom outlet or sometimes install the short sluicing tunnels can be applicable to passing density current. And the last one is sometimes categorized is excavation work to take a sediment from upstream and sometimes dumping. But now important challenge is how to sediment replenishment to the downstream to connected sediment deposit excavation work with downstream supply. So this is like a important, also important challenges, how to sediment routing mechanical way, also some similarity in the bypass hydraulic way. Okay, so next discussion is if some dams upstream will change the mode, it means sediment supply from upstream dam to the downstream. How will it impact to the downstream? This is important questions. So usually conventional dam reservoirs trap all sediment. Of course, fine sediment have a chance to passing through, but usually coarse sediment will store or deposit here. And sometimes the downstream dam reservoir owner will be very happy because no sediment coming and no excavation or some additional maintenance cost. So let's say upstream dam will save the life of the downstream. But if we change the mode, upstream dams will start sediment routing, several methodology, bypassing or routing, flushing, many or sediment replenishment can be conducted. Those sediment will come to the next dams. So next dam owner is not so happy because additional cost will suddenly happen. And if those sediment is needed to excavate or sluicing, and those sediment will go to next dams. So this kind of cascade system issues. So important question is how to optimize those sediment routing in all reservoirs, not only one reservoir. How to like sharing the concept or strategy, and how to maximize sediment routing efficiency, because those sediment finally go to downstream, river channel or river mouth or coastal area. So how to sharing the concept, how to sharing the cost, and additional cost, how to share all stakeholders. And another point is minimizing adverse impacts. Of course, like a river environment means like a high turbidity. Marty already explained like at the previous presentation. That is not so sediment management, but the fine sediment is creates sometimes like turbidity. And sediment coming, the fine sediment like a deposit on the riverbed. So sometimes the environmental adverse impact already sometimes occur. And the coarse sediment also coming, the riverbed aggradation sometimes to increase the flood risk. So the local people downstream area is sometimes worrying about the newly coming sediment. And another point is maximizing environmental benefit. what is the environmental benefit? Is already 30 years, 50 years already passed after completion of upstream dams. No new sediment coming. So sometimes this area or this area is very much changed the environment point of view. But the newly coming sediment has a good chance to recover the original meandering or bar structure or habitat structures. Those sediment is very much beneficial to recreate such kind of dynamics of the riverbed conditions. So how to sometimes also riverbed degradation, incision, or finally the coastal erosion already occurred. Those elements is very much beneficial to recover those issues. And another issue is, let's say, reservoir life. Upstream dam will be directly effective to extend the downstream reservoir because there's no sediment coming. So if we consider 1 to 3 reservoirs, number 1 reservoir is totally received the sediment, so very much rapidly lose the storage loss. But the number 2 and 3 is extend the life because of upstream dams. But if upstream dams will start sediment passing through, so number 1 dam is extend the life. This is a primary objective for sediment management. But these sediment coming to the next dams, so number 2 dam is sharply increasing the storage loss, fast storage loss. But maybe X dams is to do that something. Then those sediment for the reservoir extend, life extend, and those sediment is coming to the next dams. This kind of like some extended or connecting issues. How to minimize those issues or how to maximize the objectives. This is very much important. Okay. So I'd like to move to the several case studies. In the first one is Rhone River cases. 2 major dams is upstream the Verboa Dam, and the second one is Genesia Dam. Upstream is Lac Leman. So sediment coming to the tributary and clear water is coming to the Verboa. And periodically, let's say every 3 years, sediment flushing conducted, and those sediment coming to the Genesia Dam. And these 2 dams is connectively sediment sluicing flushing operation. And the critical question is how to minimize downstream habitability and cause sediment deposition in Genesia dams. So this is like a diagram from Lac Leman to the downstream to the Lyon. Here is Verboa and Genesia. And this topic is already like periodically like presented by the CNR, Christophe Peterou. As far as I know, the reservoir sediment management is 2 dams is almost coordinated drawdown, but critical discussion how to get the suitable timing for upstream Verboa and downstream Genesia. And another discussion is how to minimize high turbid condition. So Genesia is a little bit high dams. They are using their surface low concentration flow and coming bottom high concentration flow, how to mixing to reduce the concentration to combining 2 like a flow to layer flow. Okay. And the second one is Kurobe River in Japan. We have 2 dams is sediment flushing, sluicing in Dashidaira and Unazuki. But the upstream dams, including Kurobe Dam, maximum dams, highest dam in Japan is this dam is at the moment no like a direct sediment management objectives. And the critical question is how to effectively transport coarse sediment, these 2 dams, and minimize storage loss, and finally those sediment to supply to the downstream river and the coastal area. So these 2 dams is located total downstream, and these 2 dams is very close to the river mouth and the coastal area. This is upstream Kurobe Dam. And this is a schematic view of a drawdown operation. The two dam is like almost coordinated drawdown and passing through the all sediment. So currently, this operation is conducted in the rainy season in June, July, and natural flood timing is suitable for flushing because to minimize environmental impacts. But nowadays is we already slightly discussing because Unatsuki Dam is a little bit large reservoir and already started coarse sediment deposit in the reservoir. How to maximize sediment, coarse sediment passage? Maybe we should slightly modify this operation rule. For example, Dashidaira Dam will be some delay and Unazuki Dam will fast to draw down because Unazuki Dam is maybe double volume, so it will take a longer time. So Dashidaira Dam will slightly wait and discharge from the upstream dams and encourage or accelerate sediment passage to the downstream. This is now is undergoing. We are discussing. Maybe we can make a presentation about the good results this kind of modification. So, and this is a result of how sediment passage, bed load material from the two dams, and fine sediment passage. Currently, almost all sediment is passing successfully, but some still blocking or some deposit is occurred in the Unazuki Dam and the downstream like channels. So how to accelerate the transport to the downstream is still we are discussing. Okay, so and this is another two cases. This is Mimi River in Japan. This dam is already 3 dams is started the sediment sluicing after modification the spillway gates. So still critical question is how to effectively transport coarse sediment through these dams, minimize sediment deposit. And sometimes the upstream sediment is increasing the flooding risk. So equivalent state is very much important. So after severe flood in almost 15 years ago, this program is started. Then it now is almost finishing the sediment passing operation. And this is before the starting the modification, this after the modification, this kind of like a deep spillway gate is conducted for partially drawdown and sediment sluicing operation. And because of that is a fine sediment originally passing, because these two dams is originally not so high dams, and the sand materials and the gravel more coarse sediment is now is increasing the passage. This is very much beneficial for save the life of the reservoir and the sediment supply to the downstream. And additionally, we should consider which timing we will conduct this kind of operation. Because in Japan, we have a kind of like a recommendation, this kind of sediment passage should be conducted in the flood period, not the normal period. To do that, we should have the rainfall and the runoff prediction during the tropical typhoon attacking or rainy front is approaching. In this case, we need some good collaboration with weather prediction and rainfall prediction and how to input for rainfall runoff process or modeling. So drawdown, this is I take from this map from the Morris Reservoir Segmentation Handbook. And this kind of sediment sluicing should be conducted with upstream rainfall events. So we already started many discussion with updated methodology. For example, because typhoon is approaching, but sometimes uncertainty still exists. So if we can start or decide this kind of drawdown operation, we need a couple days needed before starting. So such kind of ensemble prediction data can be like a very much good guidance to detect the suitable timing or how much percentage we can hopefully start or not. Or drawdown, after drawdown, we should recover the water storage. Such kind of issues now is very much like an important point. This is an example is like a Mimi River. Mimi River is located in Miyazaki Prefecture. So this kind of drawdown and the recovering, this kind of like operation should be good conduct with this kind of prediction, rainfall prediction. And the last one is a new project in Yahagi River in Japan. The critical question is how to effectively transport coarse sediments through downstream dams to minimize storage loss and the flood risk on each reservoir area. So this river basin is upstream dams is the Yahagi Dam and connected to several dams downstream located. And the new bypass system is now is under planning. The 8 kilometer and the 500 cubic meter per second is because just below dams, additional dam is located. So this bypass is connected total upstream to the downstream. And the important question is after these two dams, we have several dams downstream. So if we can divert the sediment, those sediment is going to the next dams. How to consider these sediment coming and the deposit, and how much size of sediment safely passing, or how much size or how much volume will deposit each area. Of course, we already discussed with downstream dam owners, companies, and how to optimize sediment management objectives. Of course, these sediment can be excavated and utilized for construction materials because historically we can utilize those materials very much good quality. But if intensive sediment deposit, some flood risk or management costs needed in those downstream area. So how to consider those sharing the maintenance costs is very much important. And finally, those sediment is going to the downstream coastal area. How to beneficial, because downstream fishery issues very much cross connected to this kind of sediment supply. So this kind of basin scale integrated management is needed. So this is like before the sediment bypass installing, and after sediment bypass, this area is increasing some deposits. So excavation or another sluicing methodology needed. Okay, so today's my topic is how to consider this kind of cascade issues and how to increase bypass sluicing efficiency and minimizing additional sediment management costs is very much crucial. So to do that, we need updated methodology such as dam upgrading, some technology, for example, spillway gate design or new bottom outlet or bypassing sluicing, how to linkage upstream action to the downstream actions. Of course, some traditional mechanical or hydraulic dredging or excavation and some tracking, conveyor belt actions we also discussing. And rainfall land issues very much important to optimize cascade issues because it's not single dams. It's a catchment scale we should conduct effectively. And the last important point, how to share the costs. This kind of guideline. Currently, this is guideline did not exist. So how to share the concept and the basin scale, integrate the management, how to collaborate. This is important for all stakeholders. So thank you very much for your kind attention. This is my end of my presentation.
Thank you, Professor Sumi, for the wonderful presentation. Any questions, please?
Can I talk?
Yes, please.
Thank you. This is Hirofumi Okumura speaking from Japan. It's not a question. I'm saying about my thought. Cascade system is good for power for generation or water use, but on the other hand, it's difficult to control the sediment, and then sometimes dam owners are different in one river, and I think we have more discuss between the owners of dams, and we are trying now. Thank you.
Yeah, thank you very much, Okumura-san. So, my message is, what kind of guideline should be prepared?
What kind of guideline?
Guideline.
Now I don't have a question. Now I'm trying to make rules or good system, and we don't talk about sediment control in river, but in just one dam. So I'm sorry, I don't have idea of the rules.
Okay. Yeah, thank you very much. Yeah, because today's my topic is maybe I would like to discuss with Marty and the other members of technical committee of reservoir sedimentation in Icold, because maybe the next step, how to share the this kind of cascade dams sediment management concept, and if we have good examples in the worldwide, because maybe we have many examples in Japan, but still struggling how to share this kind of concept. But maybe other countries is if some good hint, those hints should be like summarized as a next bulletin like that. That is my message.
I agree with that. There's many systems where even though we're used to looking at one dam at a time, really it should be more of a system approach, looking at the whole river system. And for your example, and also here where I live, delivery of sand to the coast is very important because we aren't replenishing the beaches, so there's coastal retreat, and that's a problem. So you need to consider the series of dams on the river, not just one at a time. So that's important. And then I was just going to comment the example with Jenisat Dam on the Rhone. Part of the problem there also, or I'll say problem, but difficulty was you also had two different countries, right? You had Switzerland and France, and they weren't always coordinating. At least in the past, they had some issues in terms of how they weren't coordinating the releases and doing that management. So not only different companies maybe on the same river, but different countries with even different regulations in terms of what's allowable for releases. So it can be complicated. Thank you.
Yeah, thank you.
Just to add, Professor Sumi,
Yes.
to ask for the guidelines, it's extremely difficult because these dam owners are different. And I can quote you a very simple example. I was managing till maybe about 4 months back, I was managing the largest irrigation system and the 3 big dams in India. And there was a lot of sedimentation problem. And when I said that being head of this organization, when I posed this problem to the partner states of the different states in India who were problem to them, a very funny reply came. They said, take this money from the upstream state from where this sediment is coming. so because without understanding the issues, but we have a good example in Norway. I think I was in Norway long back, and there they have these basin authorities. And Basin Management Authority is the one which decides that the downstream, if there's a dam coming up upstream, then to some extent the cost of the dam has to be borne by the downstream people. And all the decisions with reference to the dams on the river, where when you carry out the flushing, when you carry out the sediment bypassing or whatever, they are ultimately taken by that Basin Management Authority. So which is, I think, a good concept which need to be followed. But maybe it is again the becomes difficult because each country and each state has their, within the country also, these different provincial states, they have different set of rules for themselves. So it's quite a challenge. So any further questions, please? Okay, so if there are no more questions, we go to the next presentation by Dr. Nicholas, World Bank's Global Study in Sediment Management for Storage and Runoff the River Projects. Dr. Nicholas, please.
Thank you, Mr. Chairman. Can you see my screen, first of all?
Yes, we can.
Great. Again, many thanks, Mr. Chairman, honored panelists, dear audience. Good morning from Greece. And I am Nikos Eftimiou. So in the next few minutes, I would like to give you a short overview of the World Bank's Global Study in Sediment Management for Storage and Runoff River schemes, which runs under the hydropower facility of ESMAP. Before we start, we would like to acknowledge the financial support of the Austrian government and the Ministry of Finance, which provided the funds for this study. This financial support has been initiated through discussions between Professor Helmut Habersack and Mr. Praven Karki, who is the global lead of, for hydropower and dams in the World Bank. Marty Till gave a great overview of the reservoir sedimentation issues, the impacts on the performance of hydropower and flood control, fresh water supply. And if we consider also the reduced rate of dam construction throughout the world, combined with the storage loss due to sedimentation, all this currently result in more storage being lost annually than added. Climate change will also impact further the performance of the reservoirs through the increase of the intensity of flood events and the duration of the droughts. And therefore, it is necessary to focus increasingly on storage conservation. This need has been identified by World Bank and was the motivation for this program, which has the objective of improving our understanding of the impacts of sedimentation on the economic and physical performance of storage schemes and runoff river hydropower projects, and to support the planning, the implementation, and the operation of effective and sustainable sediment management in this type of schemes. The program has 5 activities. The first one includes the development of case studies, publication of an e-book, and the setup of an international sediment management network. The second is addressed to the engineering community through development of design guidelines and the technical toolkit. The third is more addressed to the decision-making community through development of guidelines for sediment management policies, recommendations for such policies. The fourth includes capacity building and knowledge transfer. And the fifth was a demonstration, a demo of a sediment management study in an existing reservoir in Philippines. Before we start, I would like to emphasize that I speak on behalf of the Global Sediment Management Study Team, which includes many firms and consultants. We shall start with the World Bank peer reviewers working also on this project, the University of Natural Resources and Life Sciences in Vienna, Boku University, the International Hydropower Association, Stanford University, the University of Philippines, Diliman, and the International Hydrological Program of UNESCO. We are working also with a large team of consultants, including George Annandale, Gregory Morris, Professor Helmut Habersack, Dr. Michael Trithard, numerical experts, sediment monitoring experts. So colleagues that have dedicated their work life in sediment and sediment management. All this runs under the lead of and the leadership of Pravin Karki, who is a global lead of hydropower and dams, and who is the heart of this program. Without any delay, let's go to the first task of the Global Sediment Management Study, which is the case studies. And we will publish approximately 15 reservoir case studies and 3 basin case studies to describe and analyze sediment management strategies at selected operational hydropower plants. This is done in coordination with hydropower companies and international organizations, and the case studies will describe both successful and unsuccessful approaches. The idea is to draw lessons from real-life examples. The case studies will range from dams with storage reservoirs to run-of-river projects, from small to large-size hydropower plants, and they will cover a wide range, both geographical and environmental, that will go from major mountain areas in Alps, Himalayas, to lower relief regions. The second task is the publication of a sediment management ebook. The idea is to help convey the sediment management message. And we want to develop an interactive ebook that will emphasize modern data visualization through photography, story maps, and infographics, and will be prepared to display the major concepts of sediment management, its long-term benefits, technical strategies for implementations, requirements for success, including monitoring, and suggested policy directions. This activity will be addressed to a wider audience, as said, to convey the importance of the message. The third task in the first activity is the setup of International Sediment Management Network, HydroSedinet, which has been recently inaugurated. And here you can see some glimpses of the web-based platform of this network, which is open in the public domain. And the idea is to foster collaboration before different stakeholders involved in sediment management, to connect different initiatives in this area, to disseminate news, resources, publications. And as said, it's important that it is without membership fees. We want to make it free to everybody interested in this topic. The second activity includes the development of design guidelines and a technical toolkit. The first task is to upgrade and finalize, to develop an Excel toolkit, reservoir sedimentation, named reservoir sedimentation, RESET, the abbreviation. This is developed by Greg Morris in collaboration with Boku University in Vienna, and it will include a collection, a suite of 5 technical analysis tools that will enable assessment of sediment yield through development of sediment rating curves, assessment of physical properties such as mass to volume conversion of sediment deposits, estimation of sediment trap efficiency, assessment of the sediment impacts or sedimentation impacts on firm water yield and power production, and assessment of long-term reservoir capacity. On the right-hand side, you see an example of a technical analysis tool that has been developed for the assessment of sediment yield through sediment rating curves. And in the middle, you see an example of the documentation, how to use, what data are required, how to set up these technical analysis tools for the performed analysis. The second activity is the upgrade and finalization of the reservoir conservation model, abbreviated RESCON2. And here, so we are developing a new graphical user interface that will enable a much more user-friendly and easier model setup. We are implementing many graphics. We are improving the computational algorithm. We are adding new functionalities, such as the assessment of a combined strategy that enables the analysis of different techniques applied either simultaneously, concurrently, or sequentially. And it includes also a climate change analysis for the assessment that allows conducting a climate stress test in order to test the sensitivity of the project performance for assessable rates of future climates, allows the assessment of the vulnerability of the facility to different climate futures, and finally, it allows a robust decision making in order to find the sediment management techniques that provides robust adaptation to climate change under acknowledgement of the uncertainties associated with the climate future that will be realized. The third activity, the third task in this activity was the development of surface erosion modeling guidelines. This is to assess, to help the performance of catchment management studies. And here we've been working together with Stanford University and Dr. Raphael Smith for the development of a guidance note that provides guidance on surface erosion modeling approaches under various data availability conditions and project development stages. It includes fact sheets for different surface erosion models, including information on necessary input, type of output, some pros and cons for the application of these models. And it includes also a decision tree to identify candidate catchments where surface erosion could be modeled using numerical tools. The third activity of the project is the development of a guidance note for policy guidelines on sediment management. A comparative analysis has showed this work is conducted by Dr. George Annandale and Usaid Kasevit in World Bank. And as said, so a comparative analysis has showed that significant policy gaps in legal and institutional frameworks are found worldwide. In this map, on this slide, you see with dark color, with dark blue color, the countries where are no policies or very limited policies, and with light green color, countries with existing policies or practices on reservoir sedimentation management. As we can see, so the countries with existing policies are quite few compared to the rest of the world. So the current policies and the institutional frameworks, they perceive reservoir dams as an exhaustible resource, and they are not usually sufficient for sustaining their longevity and function. So this is a sign that we need stronger reservoir sedimentation policies that would seek to minimize the rate of volume loss and to achieve to the biggest possible extent an equilibrium between sediment inflow and sediment outflow. So a set of policy recommendations has been developed by George, and it covers the principal topics shown on this slide, including governance, assessment, prioritization and scheduling, guidance for engineering for during operation of reservoirs, environmental and social implications, economic analysis, and sediment monitoring. The fourth activity included capacity building and knowledge transfer. On the left side, you see the before COVID situation. We have organized many workshops, trainings in different countries. And on the right side, you see the after COVID situation, where a large number of webinars has been organized again on the same topics. With large participation, approximately 400 engineers, decision makers, managers have joined these webinars and workshops and have been informed about reservoir sedimentation and sustainable sediment management. We always encourage the participation of students and researchers in these workshops in order to spread the word for this very important topic. The topics covered in the workshops, webinars, trainings are reservoir sustainability and policy guidelines, the impacts on the operation of storage and runoff river schemes, innovative and of course the state-of-the-art approaches for sediment management. We provide hands-on training on RESCON 2 for analysis, rapid screening of sediment management alternatives based on historic hydrological conditions, as well as for the how to perform the climate change analysis. We talk a lot about sediment management as an adaptation strategy to climate change, and also an introduction to numerical and physical modeling. So approximately 10 workshops, webinars have been organized so far, addressed to different audiences. The second activity here is a collaboration with UNESCO's World's Largest River Initiative, working here with the International Hydrological Program and the Institute of Professor Helmut Habersack in Vienna. And the main objective is the development of a standardized methodology for the description of the status of large rivers. Here on this slide, you see, so first, this includes the collection of different types of parameters that cover different thematic areas, ranging from hydrology and hydraulics, water quality and ecology, sediment transport and morphodynamics, and river management and socioeconomics. In order to describe the status of large rivers, these parameters are further analyzed and processed in order to cover different scales, going from river basin scale up to local scale on river cross-section scale, different spatial scales. We can divide, for instance, the river course to upper reach with steeper slopes, reaching down to lower reaches and deltas, and of course temporal scales. So we can analyze data, the historical development of the measured data, present the present status, and try to show some future trends if they are apparent from the historical data. Just an example here for Danube River, so data that have been collected and processed. So on the left side, you see this is the development of the sediment yield. So this tree chart shows the unit is expressed in million tons. The width of each branch of this tree chart shows if we have the wider, the more sediment in the tributary arriving to Danube River, and the thinner, so the less sediment. What we can see is a reduction of the sediment yield over time, and that goes from approximately 65 million tons to 20 million tons. Also, data are collected and presented on coastal erosion. For instance, here you see the mouth of Danube River in Black Sea, where coastal erosion up to 25 meters per year, 24 meters per year, has been observed at different locations. The idea is to present this data in order to emphasize the importance of sediment, what are the impacts of sediment trapping, and why it is very important to achieve river connectivity and sediment transport continuity along the rivers through implementation of sediment management in reservoirs. The last activity was the elaboration of sediment management study in an existing reservoir, runoff river, used for a daily picking in Philippines, in Mindanao, Philippines. This is not a design study. The idea is to develop a study strategy and to identify alternatives to be modeled. It included also a field data collection, a monitoring campaign. Numerical and physical models have been calibrated on basis of the available field data and historical data, and different sediment management alternatives have been tested in the models. As here on the right side, you see schematic layout. On the upper side, you see the pondage of the daily picking runoff river scheme. On the left is the power waterway, and on the right side is the river course moving down downstream of the dam. So the study defined the sediment management problem, highlighted the types of management actions most likely to be successful, and also identified important gaps in available data. Just to give you highlights of this work, so a monitoring campaign was performed. We organized a test sluicing event in order to see how the reservoir behaves hydraulically and to collect hydraulic, hydrological, and sediment data that have been used for the calibration of the numerical and physical models. So on the left side, you can see the location of where instrumentation was installed. Here has been measured the river bathymetry before the reservoir bathymetry before and after the test sluicing event. And of course, laboratory tests have been performed in order to determine important physical parameters obtained from the samples that were obtained during the monitoring campaign. For example, here at the lower side, you can see shear stress tests performed in cohesive sediment obtained from the reservoir. Finally, we performed the team performed different types of numerical of modeling. This included surface erosion modeling at the upstream catchment for the assessment of the sediment yields arriving at the reservoir. So it included a 3D numerical modeling of the reservoir with the model ISET developed at the Boku University in Vienna. Here you can see an example of this modeling and the bed level differences calculated for a specific studied sediment management scenario. And we performed also 1D numerical modeling for below the dam in order to assess the transport capacity of the river and if it is able to accept when an equilibrium can be expected to be reached. So the last step was to design, construct, and run a physical model of the reservoir in order to study more in detail sediment management alternatives that have been previously modeled. Having said that, I would like to thank you very much for the attention. So the global sediment management study reaches slowly to an end. Within the first semester of 2021, we expect that all activities will be completed. And the team is more than happy to connect and share the products and knowledge obtained during this very interesting project. Thank you very much. Mr. Chairman, over to you.
Thank you, Dr. Nicholas, for giving global overview of sediment management and the problems being faced. We in India are asking the dam professionals and the youngsters connected with management of the dam to join the SEDINET, and I have talked to the management of the water management companies, to their CEOs, that I write to them requesting all these youngsters to join this global World Bank initiative. Thank you. Now we have a next presentation. Any questions, please?
Can I? Okay.
Yes, Professor Sumi, please.
Yes. I have one simple question. You summarize or mapping the availability of policy of sedimentation in the reservoir sedimentation management in the world. So my question is, how did you get some criteria, several criteria or several aspects? What kind of policy is available? What kind of policy should be prepared? Could you explain the contents of the policy?
So first of all, I would like to guide you to the George Annandale and Usaid Kasevich, who are the team members that dived deep for this activity. And what I could tell you is that has been performed detailed research, internet research, and through the archives of World Bank for the developed policies on reservoir sedimentation management. It's important that we differentiate between sediment management or catchment management policies and reservoir sedimentation management, because actually there is a big gap. And so there has been a thorough research in order to see what has been developed in different countries. And so now about the criteria used during this research, I think that the colleague who performed this task would be more appropriate, and I would be happy to share the contact details. And the contents of the policy guidelines, they start from the importance of the topic, the sustainable development, what are the challenges, why it is important that we deal with this problem. And they cover different aspects. So engineering, environmental, how we value the benefits of reservoir operation, not only for our generation, but also for the next generation. So they give, first of all, it's not policies, but it is just a collection of guidelines, what could be included or what should be considered during the development of such policies. And again, here, of course, George Annandale, who has worked a lot on this, will be happy to share relevant information.
Nicholas, I have a question. The products that you indicated that were part of the outcome of that study, are those going to be available in one spot, HydroSedinet or somewhere else, or you have to go to different places? World Bank for one, and where do you find these things?
So for sure, on the website of HydroSedinet, so the technical analysis tools will be published. For the policy guidelines, I think that there, so it is important to discuss with Mr. Pravin Karki. so for the dissemination of this deliverable. And the case studies will be published in the Sediment Management Hub of International Hydropower Association, who works for the development of these case studies. They will be a little bit scattered, but they are well-known hotspots, and we hope that hydrosediment will become also one of these hotspots for sediment management.
Professor Sumi, you were saying something. Your mic was under mute. So if you want to add something, please do that.
Okay, thank you very much. My point is important policies or guidelines, including the data collection. How often or how precisely take data as a bathymetric survey is one point. And the planning stage is how much sedimentation volume should be prepared at the beginning. And last point is sediment management means how much sediment should deliver or supply to the downstream. Yeah, EU already started some bed load connectivity already discussed, but this is very much like a advanced one. But the other country, even Japan, is such kind of like a sediment supply policy is not available at the moment. But how to discuss that point is also very much important for future. Thank you very much.
Professor Sumi, you are absolutely right. So one thing that I neglected to mention is that sediment monitoring is a very important aspect for anything you do. So without correct data, it's castles on the sand. Also the environmental requirements downstream are very important. And so, of course, we understand that it's not possible to develop guidelines that say this is correct, do it like this. But so this work wants to give guidance on what should be included in such policies. And all this that you mentioned are included, and we would be happy to connect together with George Annandale and Mr. Karki, and to discuss further this issue, and of course the experience that you have in Japan through such policies and others, of course.
Yeah, okay, thank you very much.
Okay, so we move to the next paper, International Reservoir Sedimentation Management Practices and Experiences by Hans Sengrov.
Good morning from Copenhagen. Let me see if I can share my screen.
Yes.
So can you see the screen now? Okay, I took that as a yes. I couldn't hear.
Sorry, yes, we can. Thank you.
Okay, thanks a lot. And thank you for being part of this fantastic session. I think it's quite interesting. So my presentation today is lined up here, and I believe my contribution today will be on some of the part which also need to be considered when we talk about sediment management, namely economics around it. And integrated sediment management is not just about the physical sediment, but it's also across disciplines and across sectors. So that's really about reservoir storage and usage. Of course, about sediment and impact, I'll say a few words about sediment management practices also, and not least about a roadmap for individual dam owners. My background is I worked for many years for GSI, which some of you may know. and I'm engineering in river hydraulics and sediment. Worked for many years in South Asia. Lived there also. I was managing director of DSI India back in 2011-13. So therefore, my presentation will actually focus a lot on India today. You may have seen this maybe many times, I could imagine, but it shows reservoirs throughout the world and the storage capacity. And reservoirs are really essential in arid areas. I think also, as Martin pointed out in the beginning, for irrigation, of course, but also for global electricity. Energy is accounting for 20% of the global electricity, and not least for flood control also saves lives every year. It saves a lot of property. So reservoirs are really essential. But we also see that there's a lot of scope for more reservoirs also. Talking about India, only 1/3 of the potential is actually utilized today. But there are also challenges with the use of reservoirs, of course, and sediment is one of them. And it's unlucky that sediment is actually taking up storage space. So that's a good place to start to make sure that we're not unnecessarily occupying space, storage capacity due to sediment. So the first kind of very important use of reservoirs I would like to highlight is for irrigation. And I've done some calculations and trying to put up some numbers because at the end of the day, economics is just a very, very important part. And looking at the cereal production, which is mainly wheat and rice in India, we see that the total production comes up to around 240 million tons. And we have around 250 billion cubic meter capacity in India. But if we convert that into numbers, to dollars, using some kind of a standard cost, here I've used $260 per metric ton of wheat, then the storage capacity can basically be converted into billion of US dollars. And I have come up with a number here of $50 billion of food production from what's called reservoirs. And that's difficult numbers for one dam owner to relate to. But if we just convert that down to, let's say, a 100 MCM, million cubic meter reservoir, it comes up to $14 million US dollars revenue per year. And again, look at what kind of sediment is occupying these cubic meters. Hydropower is another very important area, and India today is actually the world's 5th largest hydropower producer. And the installed capacity is only around one third. Again, if we use a given tariff for megawatt hours produced, we can convert the energy produced in India, which is around 150 terawatt hours. We can convert that into some amounts in rupees or in billions of US dollars. And here I've found it's around 11 billion US dollars, just to come up with some numbers. Here, of course, it's more difficult to relate this to cubic meter of water, because it also depends on many other things. Of course, the head, but also the possibility of peaking and so on and so forth. But again, if we try to relate it to one individual reservoir, and here I've taken an example of a smaller runoff river reservoir, I've come up with something around $7 million per million cubic meter storage capacity. Example is flood management, and here we can look into estimated cost of flooding. There are different studies available, and some have estimated that the cost of the flood year 2018 was around $13 billion. It's very difficult to calculate, because what is the cost of life lost, for instance? But these are some estimates, and there's another study showing that the annual average flood cost is around $7 billion. And again, if we try to relate this to the installed capacity in India, it's really rough numbers, I know, but then we can divide it up to the 250 billion cubic meter of capacity and come up with some numbers. Per billion cubic meter, or if again we look at one reservoir, and we could say a 100 MCM million cubic meter reservoir, then the average cost saved would be $2.8 million. Rough estimates, I know, but now at least we have some numbers, some economic numbers to use. This graph here to the right shows the variation over the year of the actual storage of water in India. This is an overview provided by Central Water Commission, which they do every year, for the reservoirs they are monitoring. And the scale is from June at the left side to May at the right side. So the rise you see is, of course, the monsoon season. And the storage of water here, of course, reflects the physical, the rainfall and so on, but also the use of water. And again, if we're looking at these three different objectives, irrigation, flood management, and power production, they have very different objectives. Say irrigation, we want to have the reservoir completely filled up at the end of the flood season, and then at the beginning or at the end of the growth season, the reservoirs should be emptied. Then you utilize it fully. If we look at the hydropower objective, then the need of electricity can be assumed to be the same throughout the year. So therefore, we want to have a steady, the same kind of reservoir elevation throughout the year. And if we look at flood management, then of course you want to have as least water in your reservoir at the beginning of the flood season as possible, but also towards the end of the flood season, you still want to maintain some kind of capacity if there is one extra flood coming just after we were expecting the flood season to be over. And that exactly that issue is very often a problem. It was a big problem in Maharashtra in 2019, where there was a very late flood coming up in August and September, causing big flooding in Maharashtra. And that was because there was another objective also for irrigation purposes. So the reservoirs were basically filled at that time. Okay, so that was about how to use the reservoirs. Sedimentation rates have been discussed already and shown, I think, by Martin. So I'll not go too much into that. Just mention that, of course, there is a lot of spread throughout the world, but also in individual countries, and also between smaller reservoirs and larger reservoirs. But overall, it's around 0.5 to 1%. If we go to the next slide about reservoirs in India. Then I think also it was mentioned in the beginning by Mr. Sharma that this is a growing concern in India about this, also because the reservoirs are getting older. And the left diagram shows the age of reservoirs in India, and a lot of them were constructed in the 70s and in the 80s. So it is really now that you start to see reservoirs starting to be filled up with sediment. On the right side, you see some examples of different reservoirs in India and the percentage of lost storage, life storage capacity. And you see there are some of these reservoirs, they are even above 50% of lost storage capacity. So this is a growing concern. About sediment management practices, it has also been discussed earlier. I'll not go much into that, but it's absolutely important to look at the different aspects of it and look at it in an integrated manner. Erosion control, desiltation. If we have all these reservoirs which are almost filled up, we have to consider some big capital dredging or whatever we're going to do. The desiltation has to be considered. But hopefully it could go into recurrent sediment operations so that you have a kind of equilibrium in the end, and then you will have a sustainable sediment management strategy. One of the big challenges with desiltation is to dispose the sediment, what to do about it. And in India, we have a challenge that there's very little space available. There's a lot of people all over the place, and it's used for agricultural land. And if not, then it could be in forest areas, which are typically protected areas. So it's really difficult to have environmental clearances for sediment disposal for good reasons. So there has to be some solutions for that. There has to be some policies for that also. How to make use of this excess sediment. To the right side, I've just shown you this graph again about the use of reservoirs for irrigation purposes, for flood management, for power production in relation to the natural flow. And the natural sediment flow, the inflow, as you know very well, is a highly non-linear function of the discharge. So it is really during the flood season that you see all these changes in sediment in the catchment. And this will also impact the way the reservoirs are being operated. So this goes into the optimization of reservoir operation. And then it becomes very concrete for the dam owner. So the second last slide here is a kind of a roadmap. This should be much more sophisticated, of course, but it's just to highlight some of the important for individual dam owners. To get this quick estimate of the problem, the current sedimentation and the economic impact is obvious, of course. Secondly, bathymetry surveys cannot be underestimated. And we just see that there are so many reservoirs where there's some ideas about what the sedimentation is, but proper surveys are really missing. And it should be compared with old maps to assess the sediment, what's called the sedimentation issue, the scale of that. The third area is then to go more into depth about identifying the key sediment issues in that particular catchment, in that particular reservoir, and also to make some kind of economic vulnerability. And one thing is what happens right now from day to day, from year to year, but what will happen after 10 years, 20 years, 30 years. Fourth thing is to get even more into detail about feasibility studies, identifying the scenarios and then make feasibility studies, technical as well as financial. What are the best solutions? Fifth is to plan and execute either capital digitalization or recurrent settlement management. The sixth area here I want to highlight is really stakeholder involvement. And I mentioned also about the challenges with sediment disposal in the beginning. So maybe some of these reservoir rehabilitation projects could also be integrated with some other projects where you actually need sediment. It could also be working together with contractors who can mine sediment for building material or other purposes. So the stakeholder involvement is really important, and of course also people living near the reservoir. So that was my presentation. I wanted to focus on the economic impact of it, and my takeaways here is that first of all, despite the challenges, in my view, reservoirs are absolutely essential in a future green and sustainable development. Our big challenge here in the world is that we are so many people, and we are just depending on reservoirs to manage our water. Sedimentation is an issue. It's unavoidable, but it's also manageable. And there are strong business cases which will exist also for local dam owners. But on the longer term, one also has to regulate this through policies, which will also help to close the gap between short-term gains, but also long-term societal responsibilities. So we are not leaving behind the debt to the future about sediment. And then finally, a roadmap for dam owners, I think is really important. So it becomes very concrete what to do. So thank you very much. That was my presentation.
Thank you, Mr. Hans Angrop, for beautiful presentation. Any questions, please? Okay, in case there are no questions, we will move to the next presentation. Sedimentation management utilizing sluicing operation at Stoshi Dam. It is by Hirofumi Okumura. Mr. Okumura, please.
Yes. I submit the video presentation, and could you use the file?
Virtual host, can I request you to please play the file? Video presentation by Mr. Okumura. Virtual host, are you listening, please? Co-host, virtual co-host, are you listening? I'll fix it up, please. Please wait. Mr. Okumura, they are playing it.
Excuse me.
I've asked the virtual host to look into it, and they are playing the presentation. They're taking little time.
I will present my presentation on live.
That would be wonderful. Please do that.
Okay, I can do it.
Yeah, wonderful.
If you need any help, just text me. Or
Can you see my file?
yes, sir, it's perfect.
Okay,
Just put this on full screen, please.
okay.
Yeah, it's perfect.
Yes, it's okay. Please proceed.
Excuse me. Can you hear my voice?
Yes, we can.
Okay, okay. My name is Hirofumi Okumura, working for a power company in Japan named J Power, which has 45 high dams. My presentation title is Sedimentation Management Utilizing Sluicing Operation at Setoyoshi Dam. We J Power trying to change our sedimentation management from excavation to sediment sluicing. Setoishi is the first field for us. Here are the contents of my presentation. I am explaining the Setoishi Dam and its problem of sedimentation management. Then, sluicing operation rules test in 2016 and 17, and regular operation in 2018. And I am discussing the improvement of sluicing operation. The Setoishi Dam is located in Kyushu Island, which is western part of Japan. Specification is shown in the table. The Setoishi hydropower plant has been generating for 60 years, since 1958. And the plant has 50 gigawatt hour in the annual total generation, which is equal to the annual consumption of 20,000 households. Though sedimentation rate of reservoir is 8.46 low, there is an inundation risk during a flood around the reservoir. The Setoishi Dam has problems of sedimentation management. There are roads, bridges, and houses around the reservoir. The picture on the left side shows the flooding around the reservoir. Inundation risk in the Kuma River existed before the Setoishi Dam construction and after the construction. The risk has been getting more serious by sedimentation. The Setoishi Dam needs sediment management to make inundation risk lower. I explain the problems of excavation. The picture shows the excavation in the reservoir, and the table shows the actual result. Excavation has problems on not only the limitation of volume and place for excavation, but also difficulty of getting a temporary disposal area. heavy traffic of transporting sediment, long-term shutdown of power generation, and obstruction against the integrated sediment management in river basin. About the sluicing operation. First, I explain the rules. As the figure, the sluicing operation is draw down the dam water level during flood and flowing down sediment through the spillway gate, which flows into the reservoir or remained in the reservoir. To make rules of sluicing, we have executed the calculation and the result is on the slide. Horizontal axis is past years and the vertical one is sediment volume. According to calculation result, low water level minus 4.0 meter, which is blue in blue line on the graph, is selected as the sluicing water level in order to increase the sediment in the reservoir. In order not to increase sediment in the reservoir, and not to change the environment in downstream of the dam by large volume sediment from the reservoir. We conducted the test operation in 2016 and 17. At the table and the figure, sluicing operation goes with in gradual way, monitoring the influence on the reservoir and the downstream of the dam. One test operation in 2016 and 3 test operations in 17 were conducted, and they were not in large flood. In the test operations, remarkable environment changes and sediment behaviors were not found, and the weather forecast system did work well. Finally, it was determined to start the regular sluicing operation in 2018 as planned. Oh, I'm sorry. Regular operation has been started in 2018. Remarkable environment changes were not found in downstream of the dam. Time series of rainfall in first operation. Dam inflow and dam water level are on the graph. The graph shows that sluicing operation was conducted well as a result. Contours of riverbed in the reservoir were measured both before and before 2 operations and after 2 operations. Change of the riverbed in the reservoir is shown on the slide. It shows the erosion area, which are in blue, and the bed-rising area, which are in red. The table on the slide is change of sedimentation volume in the reservoir. The total is minus 153,000 to 724 cubic meters. Almost of it is near the dam because there is fine sediment near the dam. And the red area, which are bed rising area, are 5 in the reservoir. There are 2 reasons. One is that it's easily sedimented in excavation area. And the other is that it's easily sedimented in river narrowed area by deposit from the bank. These areas are shown in the photos on the slide. It needed the improvement of sluicing operation. There are 3 points. Number 1 is modification of the operation rules. Number 2 is sediment replenishment. And number 3 is removal of large rocks for water flow. Number 2, modification of the operation rules. As calculation results, the lower the sluicing water level is, the lower water level is set lower, and therefore it's rational and effective that the sluicing water level is set lower, and it should go with in gradual way. Monitoring the influence water level is set lower, and it should go and the down on the reservoir and the downstream of the dam. Number 2, sediment replenishment. As countermeasure against the less coarse sediment in downstream of the dam, it's effective to execute the sediment replenishment. The picture shows the sediment replenishment in 2018. The volume of it was 500 cubic meters. Number 3, removal of large rocks for water flow. Riverbed aggregation was found around 1,000 meters and 2,000 meters from the dam after the sluicing operation in 2018. Two figures on the slide indicate that the river width is narrowed by deposit from the bank, and there are obstacles against water and sediment flow, and should be taken away or broken into pieces. Conclusions. The sluicing operation in the Setoishi Dam was started in 2018 after test operation in 2016 and 17. In 2018, a large flood took place with a maximum dam inflow rate of 4,450 cubic meters per second in July, equivalent to a 10-year flood. It found that operation rules are functional, and it needs more couple of years to estimate the effect of operation. It's useful and necessary to prepare the improvement of get better effect of sluicing operation more quickly in river basin, coastal area, and hydropower supply. And I have some addition of my presentation. And 7 months ago, it's July 4th in 2020, we had a big rainfall in the Setoishi Dam. Volume of inflow is about 10,000 cubic meter per second, which is 1.5 times as design volume. Powerhouse was damaged and now under repairment. And the reservoir sedimentation was decreased by 200,000 cubic meter. We got some data effective for sluicing improvement, and we are studying them now. Thank you very much.
Thank you, Mr. Okumura. I think very interesting presentation, how we can use the sluicing operations for flushing out the sediments. And as you have rightly pointed out, for sluicing operations, we need to formulate the rules because if you carry out the sluicing under very low discharges, the sluicing will not be effective. The upstream fetch area up to which the sluicing effect would be there would be highly limited. But then you have to be prepared during the flood season, and then when there's a prediction for higher flood and the higher rainfall, then you have to plan for the sluicing. So maybe that is what the sluicing rules you are pointing out. But these sluicing rules probably are required to be put in place at the time of commissioning of the dam itself. So that is what I have to say. Any questions, please? Okay, in case there are no more questions, I would request the next presenter, Takahiro Koshiba, Padload Transport and Abrasion Monitoring at Koshibu Dam.
Sorry to interrupt. There's a question I'm sending in your chat box. Please check, sir.
I have not received it. Just a second before Mr. Koshiba, please hold on for a minute.
Okay.
If there's a question for Okimura, to Mr. Okimura, there's a question. I'll read for you. The question is, apart from general segment management strategies arising from general cases, flagging of payload transport, serious situation that can arise from landslides, earthquakes, gulf, etc., need to be flagged and examined for their possibilities of occurrence. This question has come to me from the virtual host. I do not know who has sent the question. Mr. Okimura,
Excuse me. Can I have a question one more time?
I'll read it again. I'll just a second. I'll send it to you in the chat box. I've sent it to you in your chat box, Mr. Okimura. Please read from there.
Okay.
Did you get it?
No, no, I don't find it.
Okay,
Checkbox.
on the on the chat box on the right side of your screen,
Chat box.
in the bottom chat box, on the right hand side at the bottom,
Yes,
there's
I checked it.
on chat. So please click there. You will find this question. I copied it for you.
No message here.
Devendra,
Okay.
please share the question to all members.
Yeah, I'll read it again. Yeah, okay. Yeah, I'll share it for all. Just a second. I'll do that.
Coming.
I see it.
I'm sending, sir. Don't worry.
Please send it for everyone.
Okay, apart from general segment strategy, arising from general cases, blocking or bedrock situations that can arise.
It's not a question as such. It's more of a probably a suggestion which has been mentioned there.
Apart from general
これよくわかんないね。
It says there serious situation arising out of landslides, earthquake, glacier lake burst outflow, which need flagged and examined for their possibility of occurrence for the purpose of sediment transport. I put it in simple English.
Devendra, can I make some comments?
Yes, sir.
Yes.
Please.
Yes.
Yeah. I think this question is regarding the a huge volume sediment coming. Maybe this Setoishi case is considering such kind of huge volume, not a constant or regular basis.
Yes.
Okay.
Yeah, because in this it's a unprecedented inflow of sediments into your reservoir because of the glow of the landslides. Normal landslides are the landslides which are induced due to earthquake.
Sluicing operation is more effective than excavation in the situation of such kind of disaster. So I think it's effective more than excavation.
Okay. Can I make some comments? Devendra?
Yes, please.
Okay.
Yes, please.
This Setoishi Dam is a kind of a semi-run of river system, low head dams. So originally deep gates they have. So they will slightly change the operation rule, more effectively passing the incoming sediment, let's say regular based sediment transport rate. And the upstream catchment is large, but in this case, it's not so dominant. This kind of like a landslide or, of course, no growth in this climate. But some cases already I explained in the Mimi River, cascade dams in the Miyazaki. That case is the landslide dams occur upstream and the huge sediment coming in that cases. So that depends on the river basin or upstream condition, how we should consider such kind of like a huge or extreme events or extreme sediment volume.
Thank you, Professor Sumi, for explaining it very nicely. And
Thank you very much.
if there are no more questions, then we will request Mr. Koshiba to please proceed with his presentation. Mr. Koshiba.
Yes, thank you, Chairman. I'm going to share my presentation. Sorry. Sorry, just a moment. My PowerPoint has freezed right now.
No problem. Please take your time.
Okay, sorry. Can you see my presentation slide?
Yes, we can.
Okay. Thank you, Chairman. I'm Takahiro Koshiba, postdoc researcher at the Kyoto University, and I'm doing research on the bedrock monitoring at sediment purpose tunnels and process limit. Today, I'd like to talk about part of my study, petrol transport and operation monitoring at the Koshima Dam bypass tunnel. So first, I'd like to introduce the sediment bypass tunnel. So nowadays, more and more reservoir face to sedimentation problem all over the world, and there are many strategies against the problem, but the bypass tunnel is one leading techniques used in Japan, Switzerland, and Taiwan, as introduced by Professor Sumi. Sediment bypass tunnel is a tunnel connecting upstream and downstream of dam, like this figure, and bypassing sediment-laden flood to downstream to mitigate the reservoir sedimentation. The SPT consists of roughly three parts. One is inlet here, this photo, the tunnel, and outlet. This is our field, Koshiba Sediment Bypass Tunnel, Koshiba SPT. Koshiba Dam was constructed in 1969, and due to severe sedimentation problem, the bypass tunnel constructed in 2016. The bypass tunnel has 4 kilometers of length. This red line, here is the inlet, and this point is outlet, with the tunnel width of 6.6 meters, 7.5 meter of height, and 150 inclination. This is one of the largest SPTs in the world. This is the front view of the Koshiba SPT. Here is the Koshiba Dam, and this part is the outlet of the bypass tunnel. This bypass tunnel is designed to bypass maximum 370 cubic meter per second of discharge, and that results in 20 meter per second of velocity. This is a photo during bypass tunnel operation with around 100 cubic meter per second of discharge. So it is already confirmed that this bypass tunnel works really effectively, but still have a major problem. Just a moment, please. That is invert hydro abrasion problem caused by a combination of high flow velocities and sediment transport rates, as in this figure. And this abrasion causes for dam owners to pay lots of maintenance costs, and also this uncertainty in the maintenance cost obstructs the construction of new bypass tunnels. So for estimating reliable maintenance cost of SPTs, the damaged volume should be evaluated, this volume. Because in general, damaged volume of this kind of concrete facility depends on the petrol transport rate. So in order to know the relationship between the abraded area volume and petrol transport rate, sediment transport monitoring during bypass operation and regular bathymetric operation measurement are conducted at the Koshiba SPT. Today, I want to focus on this topic, sediment transport monitoring at bypass tunnel, because this is relatively challenging, and there exist few applications in the world. So next question is, what are the properties required for petrol monitoring at SPTs, where high petrol transport rates and high flow velocities are observed? One is robustness, and also unmanned system is needed, because direct monitoring by human cannot be achieved here, this kind of intensive environment. And also continuous monitoring is desired to know the time series of petrol transport rate during operation. So we decided to use surrogate petrol monitoring system here. So next, I want to give a brief explanation on surrogate petrol monitoring systems called impact plate. Impact plate consists of a steel plate like this, placed on the bed of bypass tunnel, and the backside of a steel plate, there is a microphone. So when a gravel hit on the plate, the impact is recorded as a signal like this. Then we analyze this signal to extract the information of sediment transport, like grain size distribution, sediment transport rate. This system is already installed at the bypass tunnel like this. Koshiba bypass tunnel like this. Outlet, here is the outlet. What is noted should be noted here is that this part, the tunnel has curvature. So this side is tunnel curvature inner side, and this side is tunnel curvature outer side. And we expected that this kind of curvature may cause uneven sediment flow along with this direction. So in order to know the distribution along the width direction, we decided to put 5 impact plates along the width direction like this. Then next question is how to analyze these signals. Actually, there are many studies on the analysis of this signal, and generally, the analysis can be separated into these 3 steps. One, this is obtained signal, raw signal, and this is denoised, means get rid of the noise, water noise, and then change to some feature extraction, and it's passed to some function like linear regression, exponential regression, and sometimes machine learning to obtain grain size and sediment volume. But today, I do not go into the detail of these topics, but if you are really interested in these analysis, please see the references on my paper or contact me directly. Okay, I'm going on to the result of sediment monitoring at the Koshiba Dam SPT. Okay. In this study, I picked up this operation. This is a hydrograph of bypass discharge during the operation in 2016 for typhoon flood. This x-axis is time, and the y-axis is water discharge, bypass discharge. Please see this blue line. And in particular, please see this area. The bypass started the operation at here by opening the gate at inlet and close the gate here to end the operation. So we can say this period is a sedimentation operation. And this kind of operation is repeated again here. And what is important is that in this red hatched area, the flow was kept as free flow condition. So for explaining the free flow condition, a little bit going into the detail of gate operation of the bypass tunnel. This is a design drawing of a bypass tunnel, Koshiba bypass tunnel inlet. So this side is upstream, and this side is downstream of the bypass tunnel. So here already inside of the tunnel. The discharge, bypass to discharge Q bypass, is controlled by 2 gates. In free flow condition, incoming discharge equals to the bypass discharge. So the incoming hydrograph is preserved even downstream areas. In contrast, this is non-free flow condition. Here, the bypass discharge is smaller than incoming discharge. So in free flow condition, this part is open channel flow. So generally, free flow condition involves higher flow velocities here, and consequently, higher bed transport rate is observed. And also, free flow condition is preferable for bypassing sediment effectively because this higher velocity, flow velocity, provides higher drag force to sediment. Okay, now I move to the result. First, in terms of mean grain size, D50. This is the hydrograph I showed. And this is time series of D50. X-axis is time, and Y-axis is D50. And this one is time series of D50 as well, but by each impact plate, from impact plate 1 to 5. These numbers are corresponding to these numbers in this figure. So plate 1 locates the tunnel curvature inner side. Our findings here is that D50 is generally in range of 0 to 100 meters. Here, this is reasonable because the target grain size for Koshiba bypass tunnel is designed to be less than 20 centimeter. And also, interestingly, relatively large grain size was observed in free flow regions. Because as I said before, free flow provides higher drag force to sediment, so that causes larger sediment to be moved. So the free flow state is short in this operation, but this seems this short time is critical for abrasion because larger grain size causes the higher impact to the bypass tunnel bed. Next is petrol transport rate. This is also x-axis is time and y-axis is petrol transport rate. And this one also time series for petrol transport rate by each impact rate. So here what is interesting is that the consistency, the agreement with this observation and the observation of abrasion depth by laser scanning. This is the result of abrasion depth by laser scanning at the bypass tunnel around outlet. So this is the tunnel curvature. Impact plate is this side and 5 is this side. Obviously, the main abrasion is in the tunnel curvature inner side here, and also sediment transport concentrates on the tunnel curvature inner side here and here. We expect that this is because of secondary flow caused by this tunnel curvature. And this kind of observation can be seen also in other bypass tunnels. So it is good finding that we can see consistency between the sediment transport rate monitoring and abrasion depth measuring. Like this, the installation of indirect monitoring system enables us to know the spatial temporal distribution of sediment transport inside of the tunnel that cannot be seen before in any bypass tunnels. So my conclusion is that abrasion is a topical problem in operating sediment bypass tunnels, and for dealing with this problem and know the relationship between the sediment transport rate and abrasion, both bathymetric abrasion measurement and bed load monitoring are conducted at the Koshibu Dam SBT. For that, impact plate system is installed because that has high robustness and also indirect monitoring system. Impact plates provided spatial temporal information on grain size and bed load transport rate, and that shows the good consistency with abrasion observation and other bypass tunnels. So in the future, we keep going to monitor the sediment transport at the Koshibu bypass tunnel to understand the abrasion mechanism. Before this kind of study has been dedicated before, but past existing studies shows the relationship of the summed total petrol transport rate and the total abrasion. But I think by installing this kind of indirect petrol monitoring system, we can know the relationship of petrol transport rate and abrasion in higher resolution. That's all of my presentation. Thank you for your kind attention.
Thank you, Mr. Koshiba. It was
Thank you
nice
very much.
Nice study you have come out. Any questions, please? I don't have a question, but
Mr. Chairman, one question, Nikos Eftimiou. Thank you very much for the very interesting presentation.
Thank you very much.
Have you compared the measured results with the predictions of empirical models for the abrasion depth? And how was the agreement, if done? And the second question would be if you have if you could give any insight in the maintenance costs for against abrasion.
Sorry, your question is about the comparison between the observed abrasion and some calculated abrasion by empirical models?
Exactly, the first part. And the second, any insight you could share on maintenance costs against abrasion in sediment bypass tunnels.
Okay. Yes, it's dam owners are calculating the abrasion depth using empirical models, but the problem is that empirical model is based on very simple. Okay. The empirical models uses some coefficients, but coefficients are estimated based on, as I said, the total petrol transport rate and the total abrasion. And this cannot, these do not reflect on the more detailed sediment distributions. Like sorry, can you see my presentation slides right now?
I'm afraid not.
Not
We can see you, but not your presentation.
I'm sorry, my PowerPoint freezed again. Okay, so as I said, the empirical model, the coefficients used in the empirical model is based on the really rough estimate using the total sediment transported volume and the total abrasion. So still, we'd say, I'd have to say the accuracy is not very high yet, but I believe that using this monitoring result, I'd like to improve the accuracy of coefficients and possibly incorporating some impact of grain size, or some more information into the empirical model to get the higher coefficient with higher accuracy.
Nicholas, you're mute.
I can imagine that also calibration can be performed with this field data that you obtained through this method. So,
Can I make some comments? Dobendra.
Yes, please.
Okay, yeah. Your question is very much important, because Koshiba, the study is to direct measure the petrol transport rate. So why petrol transport rate is needed to input to the equation to estimate the abrasion rate. And currently, we are now comparing the several equations like Ishibashi formula conducted by Japanese researcher, and also Christian Auel. He also conducted interesting study already. So we are now comparing the several approach, and so some comparing to the, for example, some key parameters. Because we have already the Asahi bypass system is well documented, and this Koshibu Dam is a newly started operation. So this data is very much interesting to calibrate the coefficient.
It seems there's some connectivity problem with Professor Sumi and Koshiba,
Sorry.
because we are not able to hear both
Okay.
of them, and I'm afraid they have they have been disconnected or something like that.
Okay, yeah, thank you. So
It's a
important
problem
point
with
is
the network.
Network?
Yeah, there was a Professor Sumi, there was a network problem. So I would request you to please repeat what you were saying.
Okay. Yeah, okay. Thank you very much. Like, important point is Koshiba study is focusing the grain size distribution. So which size of material is the most dominant is the erosion, abrasion. So his study is this kind of like a mapping of time series and the spatial distribution of the grain size, let's say. So how to matching is abrasion patterns and total load and the grain size distribution. Maybe he's trying to develop the new equation, not only total load. Maybe he will make a presentation in the next time more detailed.
Yes.
Yes, Mr. Koshiba, thank you for your presentation. And I just also want to make a very quick comment here. I've been responsible for construction of a couple of dams. And when we designed a diversion tunnel, this diversion tunnel is designed to carry the bed loads during monsoon period as well as the non-monsoon floods. But usually we keep them open even during the monsoon period in view of the fact that sometimes the gate, if it gets stuck up, intake gate, then it is difficult to open it or lower it. So that creates more problems. So it's kept open. And I've seen in number of times that the bed of these diversion tunnels would get eroded. And in one of the cases, I found it was eroded to the tune of a meter, and it was even eroded, even the intake gate, the crest of intake gate got eroded. But in the second case, the damage was much less and it didn't propagate up to the intake gate. What I found is that there are two things which we need to look into. One is the supercritical flow. When we design a diversion tunnel for a supercritical flow, then the flow velocities do not have to be very high. Number two, and the design discharge versus the area of the diversion tunnel has to be such that most of the time this diversion tunnel flows under the free flow conditions. Second is in many cases, in your case, what you showed, the outlet structure was very well defined and the energy dissipation arrangement was functioning perfect. But in many cases, in case of temporary structures, which a diversion tunnel is, the energy dissipation at the outlet is not appropriate. In that case also, this creates problems. What I have seen is in case in one of the other dams where I constructed this dam and a diversion tunnel, where if you have it was a permanent spillway also, these diversion tunnels. If you have the flow velocities, it is supercritical but not highly supercritical. Then flow velocities are restricted, then the damage gets minimized. That's I just wanted to add.
Okay, thank you.
There's one more question I can find in the chat box, though it may not be directly related to the presenter, Mr. Koshiba. But I would say that the question is, I'll just read the question and we'll
Yeah,
see.
I can see. Yeah.
Professor Sumi, if you can read, can you answer this question? I'll read it. Can we raise the invert of intake by providing the hump for minimizing entry of sediment in intakes of hydropower projects? I'll reply it. Usually we have the intake at higher elevation, and we also provide a hump at the intake of especially these temporary structures, diversion tunnels. But also for the permanent intakes, we provide a hump at the intake structure. Second question is, sluicing is an effective way, but can we provide some system in the form of pipes or other arrangement with the walls? There's a half question written here. So I would say no. These in case where the sediment load is very less, maybe you can think of providing vortex pipes, but for flushing out the sediments in desilting chambers, but not otherwise, because the size of the bed load and the sediments is so large that these pipes which are provided with the walls get choked and may not function in the right spirit, and they get eroded also very fast. That's what I have to add here. Professor Sumi, in case you have any comment to make, please.
Yeah, I'm sorry, I couldn't catch the main point, but maybe your point is that using the diversion channel, right?
No, here the question was, there's a question here, can we raise the invert of intake by providing the hump for minimizing the entry of sediment into intakes of hydropower projects? Yes, I have replied, yes, we usually do it. But the second question, I just wanted, for the second question, second part of the question, if you can add something. Sluicing is an effective way, but can we provide some system in form of pipes or other arrangements with valves, etc.? So I would say that the pipes and valves are not effective because you cannot flush out anything through these pipes. The upstream effective effect is very highly limited. It will be limited only till the mouth of the pipe. So that's not a solution. But in case of certain desilting chambers, we provide these vortex type desilting chambers where we have vortex pipes also in certain cases.
Vortex pipe, vortex tube, right?
Vortex tubes,
yeah. Yeah, in former time in Japan, also vortex tube is studied. Yeah, this is also one example. But maybe very local scouring, not a large volume. So if we can save the around just in front of the intake, such kind of like a desilting structure or hydrous action, this can be work. But this bypass tunnel today, Koshiba explain or sluicing is to maintain the large volume of active storage volume is a more larger area. So maybe we can like, of course, finally we should combine this methodology. That is my comment. Yes. Thank you.
Okay. I think I must thank the presenters for making their wonderful presentation. And it was very interesting to know about the international practices, about the practices in Japan, and then about the Indian system, which was told by Mr. Hans Angrab. And with that, we close it here and we'll meet again at 1:30 Indian time. So I request all the presenters to be well on time. And the first presentation at 1:30 is Mr. Dheeraj Acharya. Thank you, everybody. So we are closing here and then we will rejoin at 1:30.
Thank you very much.
Koshiba, please mute.
Okay, gentlemen, please start next station. Am I audible?
Yes, sir. Yes, sir. We are live now. Please continue.
Okay, thank you very much. And we have the first presentation by, after lunch, we have the first presentation by Mr. Dheeraj Acharya. Mr. Acharya would be talking about sustainable reservoir management through sediment flushing, a case study of Betan Karnali hydroelectric project in Nepal. Acharya, please.
Am I audible?
Yes, sure.
Audible? Okay, thank you. Okay, welcome everybody again after this lunch session.
Sorry for Dheeraj, sorry for interruption. You can put it on full screen rather than having it.
Full screen.
In your presentation, just make it in slide presentation mode.
Oh, okay, got it. Now is it okay?
Sure.
Yeah, perfect. Yeah, just put it down. Okay. Today I'm going to talk about the sediment management measures that we had applied for this Betan Karnali hydroelectric project that is being designed in Nepal. I'm a hydropower engineer currently working in any engineering company, and then any engineering company is a semi-government owned company, and it has been studying the large scale projects in Nepal. To begin with my presentation, I would like to point out some of the outlines of my presentation. Initially, I'll be talking something about sediment requirements, sediment management requirements, and I'll talk about the project itself and how did we collect the data and how did we model it and the results and conclusions. And I look forward to your suggestions and recommendations at the end of this presentation. Needless mentioning about the requirement of sediment management, as I'm talking to such experts in sediment. However, as Nepal is in the Himalayan regions, and Himalayan region has been identified as one of the most susceptible to natural erosions. And till now, we have been studying only ROR and ROR projects basically, but now from now on, we have started to study the picking run of the river and storage projects as well. In this regard, sediment management strategies and sediment management prospects are more concerned, and we are looking forward to help from other experts to my work. Let's begin with starting with the project itself. Betan Karnali is a 439 megawatt PRR project that is being designed. We have already submitted the detailed design study report to our clients, and it is located in the western part of Nepal. Get the pointer. Okay, it is located on the western part of Nepal in the Karnali River. There are other projects, there are other large projects also along this Karnali basin. And the catchment area of this Betan Karnali is approximately 22,500 square kilometer, and 3,000 square kilometer of this catchment falls in China, in the Tibet region. Below you can see a chart that has been plotted showing the reservoir elevation volume area relationship curve, which is one of the major data that we need when it comes to sediment reservoir operation and sediment management. Let me describe a little bit about the project itself. There is a headbox arrangement. There are two kind of energy generation system in this project. There is a regular divergent kind of energy generation using divergent tunnel, using the headrest tunnel arrangement with the powerhouse, underground powerhouse, located some 2.5 kilometer downstream from the headbox area. While there is also a environmental powerhouse generation unit right at the toe of this main dam. There are, as you can see in this picture, there are two diversion tunnels of 9.8 meter diameter horseshoe-shaped tunnels with cofferdam arrangements, and then This is 3 HRT system of 8-meter diameter each, 2.1 kilometer length each. There is a powerhouse arrangement with other appurtenances, terrace arrangements. The basic layout of this, the section and the plan of this dam that we have designed is shown in this picture, in this slide. As you can see, altogether there are 13 spillways that has been designed, as the PMF and 10,000 usage on period flood and normal hydrology is very large. And there is a major issue of sediment management. So these spillways are called sluice spillways, and they have been designed for the sediment flushing, while the other 6 major spillways of 11 by 12 meters size are designed for the reservoir regulation, while the small spillways for trespasses during the monsoon season. Talking about we'll be using HEGRAS. I have used HEGRAS model for sediment modeling in this project. When it comes to modeling, there is always importance of data collection and validation from both from historical reports, and also project has established its own data collection stations. After that, it was followed by the geometrical file preparation and giving the boundary conditions model, simulating the results, and then checking if the result simulation is carried out in a perfect way or not, and then again doing the iterative process until we reach at the perfect simulation. Since we do not have this kind of reservoirs, large size reservoirs with sediment management strategies already adapted in Nepal, so calibrating the model without having already established data was a little bit difficult. But however, we tried to validate the result as much as possible by looking at the similar kind of literatures and reservoirs that are available worldwide. After the simulation was satisfied, after we thought that the solution is perfect and this is how the sediment is going to behave, we plotted the various plots and we interpreted the results. We have used upstream boundary condition as daily hydrograph. We had the data for 47 years, and then for the downstream boundary condition, normal depth was adapted, and for the intermediate boundary condition, water level was provided based on the rating curve of the sluice that we had designed. And different kind of transport functions were we concluded that Milan and Hassan at the end suits best for this kind of for this project. And range-based computational time steps were provided at the done iteratively. Validation of the model performance in reference to the existing projects were carried out. Talking about the data, in the Karnataka Basin, there are 3 major renowned Benighat lies in proximity to the project, and Asaragat is much more closer compared to the Benighat, and it has a good set of data for 47 years from 1960 to 2012. Data from Asaragat was used for this segment modeling. Project has established a gauging station, water level, both automatic and manual station for measuring the discharge, and then there are 2 kind of rating curves developed based on those measurements. For discharge, for water level below 5 meters, there is a different rating curve, and for water level above 5 meters, there is a different rating curve. And based on this rating curves, the sediment loads were identified, sediment loads were computed. Meanwhile, we have also established a station to measure the particle size distribution of the sediments. And then the figure on the right shows the PSD variation of the sediment that could be observed in the Bedan Karnali project. And the red dotted line is the particle size distribution that has been adapted for the sediment modeling. This is a picture showing how the sediment and the discharge measurements has been carried out from the existing trail bridge. You can see the sampler and the fish weight. This is the usual kind of approach that has been adopted in Nepal. When you talk about sediment modeling, there is always a necessity of dealing with like flushing considerations and how to adapt the flushing considerations, how to integrate the flushing considerations. this I tried of suspended load variation with response to discharge class range. As you can see that almost like 75% of this load of the total suspended sediment is seen in the range of like 1000 to 2000 MT per second, and it contributes much to the sediment load. On the right, you can see the general schematic representation of the flushing strategy that we adopted. You can see that from in the core monsoon month, from July to September, the full blowdown and flushing has been implemented, while on the rest of this month, from October to June, the water level only regulates as per the peaking requirement. We tried with different flushing strategies by changing the flushing days, by changing the duration between the flushing, by changing flushing flood, and then forced flushing flood, and finally we adopted 3 days flushing with 1800 cubic meter per second discharge, which was followed by 21 days of annual flushing interval with the forced flush of flood at forced flush at flood of 2400 meter per second. And to ensure that at the end of the monsoon all the sediment gets flushed, we gave an 15th of the September it is always flushed. On average, at 47 years, we computed the average annual flushing of 8.7 days per year. Talk about the result now. The MTTL is at 466 and FSL is at 473.3. As you can see that the profile of the bed after the flush, we are able to maintain the profile. We are able to maintain the live storage of the reservoir even at the end of the 47 year. But since this project is under study and there is no data to calibrate it, the calibration part was quite difficult. But however, we tried to approach as near to the reality as possible by looking at other other projects which has extensive annual drawdown and flushing carried out in past. For that, there is a project called Kulekhani. It is a 60 megawatt project, and it has been established and it has been in operation since long time now, and it has extensive annual sediment drawdown, as you can see on the right. And we try to reach to a point that the flushing results try to simulate and try to replicate with the similar to Kulekhani and other dams as well, and other flushing in other dams as well. As a result, we found that the England and Hansen transport equation best suits for this reservoir, and then the average annual flushing recommended is 8.7 days per year. Size and number of the inward gates and the inward level of the gates that we provided for the flushing is justified, and the minimum monsoon level 466 MASL that had been designed is okay. It was found to be okay. Reservoir is sustainable even at the end of the 47 years. And the introduction of bypass arrangements, though it was not model, but the introduction of the bypass arrangements could be more beneficial in terms of like reducing the loss frequency. And during operation phase, the sediment deposition must be monitored regularly to optimize the reservoir flushing. And physical model and mathematics survey is recommended each year during the operation period. Thank you. Hello.
Thank you, Mr. Acharya. I just have a question for you. This project is in planning stage?
It is in design stage.
Design stage. A very small suggestion which I thought I should tell you. The undersleeve switch which were provided, they are at what level? What is the hydraulic head on these under sluices?
From the full supply level is at 473 and under sluice is at 418. That makes around 55 meters.
Yes, you may like to consider higher size of under sluices and avoid your overflow spillway gates. That's my suggestion, because these smaller size under sluices are not effective. Only thing is you will have more force acting on the trunnion of your gates. So if you convert it into sluices, so that you have to account for. Just a suggestion you may look
The
into.
current size is already 7 by 8, sir. Like higher size compared to this.
Hello.
Can you hear me?
Yes, we can. In between there were some problems. Yes, please speak. What is the size
current
of under
size of the
sluices?
sluice 7 by 8 meters. Six spillways of 7 by 8 meters. Yeah.
Okay. Can see if it is, or if it is possible to increase the size further. Maybe it depends on the force acting on the gates, but you can still optimize it. It's always better to have the bigger size, and then maybe you can eliminate the some number of overflow spillways. Just a very small suggestion.
Thank you.
Any questions, please? If there are no more questions, we will proceed to the next paper by Makoto Ayodo. Analysis on sediment transport processes around estuary and coastal shoreline area, as in Sagami River Basin, to promote reservoir sedimentation countermeasures and integrated sediment management. Mr. Makoto, please.
Yes, thank you, Chairperson. I'm Makoto Hyodo from IREA Consultants Incorporation based in Japan. The presentation title has been already mentioned, so I will skip this slide. This slide shows this figure shows the Sagami River Basin. As you see, the flows are coming around the Mount Fuji. And in the dam areas, there are several dams along the main channel also. And in the alluvial area, there are a lot of weirs along the main channel. And here is the coastal area. It's called the Chigasaki Coast. There is one issue in the coastal areas. The coastal erosion has been occurring. So we are looking at this coastal erosion issues. Now, some countermeasures have been implemented, such as direct sediment augmentations on the shoreline erode and indirect sediment augmentation on the riverbed, expecting the sediments to be transported to the coastal shoreline. But there are several unknown factors, which are the sediment transport processes, particularly around the lower reaches, where sand terrace around the river mouth has been decreased and may not be much functional in transporting sediment from fluvial systems to coastal shoreline. And then the objective of this study is to propose a hypothesis of sediment transport processes in the Sagami River Basin and to discuss challenges in the future, further promoting countermeasures for reservoir sedimentation and integrated sediment management in the basin. Integrated sediment management plan for the Sagami River Basin has been published in 2015, involving various stakeholders. Some analysis and countermeasures which have been implemented are under this plan. So I will present some of the activities which have been implemented under this plan. So here in this presentation, I will provide three results and some activities that we conducted. First is we developed a numerical simulation model in order to analyze sediment transport processes in the whole Sagami River basin. And the second is we analyzed the morphological change of the river mouth and the coastal shoreline using several aerial photos data since 1961 to 2015. And the third one is that we analyzed the change in sediment transport processes during the one flood, 2007 flood, a larger flood, particularly addressing the lower reach of the river basin. This is the first result. This figure shows the illustration of the amount of the sediment transported throughout the river basin in 1915 on the left and 2013 on the right. And top two figures show gravel sediment, amount of gravel sediment transported. And the bottom figure shows sand sediment transported. So when we discuss about the coastal areas, the sand is the most important sediment size because it this determines the coastal morphological features. And here on the left, the amount of sediment transported in the river mouth is about 65,000 cubic meter per year, but it's drastically reduced to 10,000 cubic meter per year. So this is one of the main reasons for the coastal erosions to occur in this river basin. This figure shows the geomorphological changing patterns of the lower reach of the Sagami River basin. This red line shows the shape of the coastal zone and sandbars in the river mouth in 1961. And when it comes to the photos in May 2015, coastal erosions in the east coast and sandbar positions have been set back to the upstream river. Even though sediment augmentation in the coastal area around this area has been conducted with the average of the amount of 130,000 cubic meter per year, still coastal erosion has been occurring. This figure shows the sediment transport processes of the lower reach of the Sagami River basin during 2007 large flood. So this figure is a little bit complicating, so I will extract only some of the points to explain this figure. We use the calculation results and the survey results. And here, from the Sagami River, by calculation, 20,000 cubic meter sediment has been transported to the river mouth by the 2007 flood. And also there's another result in the estuary area by survey data, 21,000 cubic meter per 4 months of the sediment has been deposited here. And there is another geographical survey data in the coastal Chigasaki coast. Then the amount of 60,000 cubic meters per 5 years have been deposited in this Chigasaki coast. Even though there is a difference in the temporal scales of the results, but at least some amount of sediment transported from the fluvial system are deposited on the estuary areas and then transported to the Chigasaki coast. Now we move on to the discussion. We developed a hypothesis, proposed a hypothesis. The sediment transported from the Sagami River by flood will be deposited on the estuary area and then sediment transported to the coastal areas by coastal waves, though slowly. So if we could quantitatively evaluate the amount of sediment from the fluvial system to the estuary area in order to protect the coastal erosion of the Chigasaki coast. And also, the quantitative evaluation enables to determine goals of sediment transport processes to be achieved for integrated sediment management involving various stakeholders. This figure shows the countermeasures in the at present and the future conditions that we expect. Currently, the amount of the sediment is dredged from the reservoirs and directly transported by dump trucks with a long distance to this Chigasaki coast. And some other sediment has been transported to this area below dams on the riverbed for the sediment augmentation. These measures are currently implemented, but it's costly. So in the future, if we prove the hypothesis, we can exactly quantitatively evaluate the amount. Then we would like to change the dredged sediment, the amount of the dredged sediment to be transported directly to the Chigasaki coast could be reduced. But instead, the dredged sediment, the amount of the dredged sediment to be transported to the riverbeds below dams can be increased. Then, using the fluvial systems, the large amount of sediment could be transported to the river mouth. Then, through the coastal waves, the sediment could be transported to this coastal area. And also, there is a deposition in the sandbars in the Sagami River basin. So we could also transport this deposited sediment in the river mouth directly to the Chigasaki coast. The distance is very small, so it's more cost-effective measures. Although this option is not the perfect solution, but at least as compared to the current conditions, we could implement effective measures involving various stakeholders. Now, conclusions and future challenges. So the second one, we propose the hypothesis that sand sediment transported from the Sagami River to the estuary area has been transported to the Chigasaki coast by coastal waves. However, the hypothesis we propose is based on only one flood in 2007. Much data for longer periods needed to verify the hypothesis. And currently, actually, we have been conducting the measurement, conducting the observation measurements in the coastal areas and trying to quantitatively evaluate the amount of sediment which is needed to come from the fluvial system. That's all of my presentation. Thank you very much.
Thank you, Mr. Hello. Thank you, Mr. Makoto, for a wonderful presentation. It was really nice to understand about the sediment deposition and sediment carried out through the hydraulic process to other parts in the estuarine areas. Any questions, please?
Hello. Can I ask one question?
Yes, Professor Sumi, please.
Okay. Thank you very much. Very much like interesting presentation about overview of Sagami River sediment management system or current issues. My question is, so finally, how much sand materials should be supplied to the Sagami River to be beneficial to the coastal management point of view? Because original estimation is 65,000 in the past, but currently the 10,000 only. So how much additional sediment needed for sand material?
Yes, thank you for your question. Actually, we have almost calculated, we have almost reached the results, how much sediment, the sand sediment is needed from the fluvial systems to protect coastal erosion. Actually, it's the amount is around 60,000 cubic meter per year. That means we need to move back to the pre-dam condition. So this was the important thing. So it's not possible. So therefore, we are trying to find the compromised countermeasures, at least to maintain the coastal line to the extent possible.
Okay, thank you very much. And in that case, is maybe some difficulty is like one point is cost issues, but another difficulty or conditionality is maybe downstream river channels. How much sediment safely passing? Maybe only sand material is not so big trouble, but downstream channels, how effectively or safely passing?
Yes, important question. Thank you very much. Okay. Now the riverbed degradation occurred already, but this was mostly, of course, the reason for this, one of the reasons for this is dam construction because it traps the sediment in the reservoir, but also gravel mining was the problem. Then now we have not checked the sediment in the pre-dam conditions. What will happen when such amount of sediments are coming to this river? So I need to check. So when we think only about the natural conditions of river systems, it's okay. But the river flood management plan has been made in the condition that the degradation, riverbed degradation has already occurred. So if the amount of sediments are increased, we need to check very carefully about the increased risk of flooding.
2019 is this area is hitting the large tropical typhoon Hagibis, and big flood flow is occur. And from now on, like of course, like climate change impact is like increasing the intensity of flood magnitude. So how utilizing such kind of like events to transport sediment and like a normal or regular flood, periodical flood event, how much sediment is safely passing? Maybe 60,000 cubic meter per second is maybe average volume, but
Yes.
maybe some large events is more large sediment, but normal year is a bit less sediment volume. So how to cope with such kind of variation? So please try to estimate how to catch up this kind of gap of sediment transport rate.
Yes, thank you very much for very important point. Actually, I have not checked very well about the various situations of the flood volume. So we need to check very carefully. We are talking about the mostly talking in terms of average sediment. So we need to think of the extreme situations.
Okay, thank you very much.
Any more questions, please? Okay, in case there are no more questions, we move to the next paper by Mr. Narasimha Rao, a case study of sedimentation and sustainable plans and approaches to Nizam Sagar and Shri Ram Sagar reservoirs. Mr. Narasimha.
Presentation.
Venkata, there is some connectivity problem at your end. Venkata, are you able to hear me? I think we move to the next paper, and when we can take paper of Mr. Venkata Narayan subsequently. The next paper is by NHPC, and who will present? You will do that?
Yes, sir. I am video we are using also. Is it possible to turn from there? Otherwise, I will.
Yes, no, we can, as is convenient. We'll try to
if it
do
is
it from
possible.
here. Can I ask the virtual host to please stop this presentation by Venkata Narayan and start the presentation on case study of sedimentation and sediment management practices in NHPC power stations. Venkata, are you online? Let's stop the presentation by Venkata and virtual host. Virtual host, are you listening?
Yes, sir, I'm listening and I'm doing.
I'll request you to please, there's a recorded presentation on the paper, sediment management practices in NHPC power stations. Please play the recorded. Thank you so much. There's no volume. There's no voice. We can't hear. Manjusha, I would request you, if you have the presentation, I would request you to please make a live presentation.
Problem. We have abrasion of turbine. spillway and other dam water conductor components and decrease in efficiency of a turbine. The annual loss in generation is also due to sedimentation that has been estimated about 1% of the overall generation. We have loss of peaking availability. We have blockage of outlet causing difficulty in operation of the gates. It is one of the highest concern for engineers across the globe. This is sediment yield in different part of the world. As you can see, this is our point of interest. This is Himalayan region. You can see here sediment yield is of the order of 1,000 ton per kilometer square per year. Here I would like to give you a glimpse of power stations that is 22 number 6971 megawatt power stations in operations of NHPC. We have 5774 megawatt in construction and 13 number of power projects, about 10 gigawatt power projects in clearance stage. This is Himalayan belt, and you will see most of the projects and power stations of NHPC are located in Himalayas, where rivers carry far more sediment load than non-Himalayan rivers. For sediment management techniques, we generally adopt sluicing by maintaining reservoir level at lower level during monsoon and flushing by bringing reservoir at down at lower level. It is recommended in small size of reservoirs and also helps in clearing the trash collected in front of intakes. We provide guidelines for flushing in which we give certain discharge, which is worked out specifically for each monsoon month for every power station. We also give frequency of discharge at which we have to carry out flushing. We also observe different parameters such as hourly reservoir levels, hourly sediment concentration, hourly discharges, gate opening, and reservoir cross-section at the end of the monsoon in specified occasions. The sediment flushing procedure below, prior intimation to regional dispatch center, arrangement for observation of water level and different other parameters, instruction to powerhouse for shutting down the units, keep all the silt excluder under sluices fully open if any, lower the water level gradually by keeping all the gates equally open, achieve minimum possible water level in the reservoir, and allow flushing till sediment concentration in upstream and downstream location is of the same value, and then we raise the water level in the reservoir by closing all the gates. These are photographs showing reservoir flushing in different reservoirs. We also provide desilting chambers in which for removal of sediment, sediment particles to avoid the entry of sediment into the turbines. They are generally designed for 90% removal of suspended sediment particles of size 0.2 mm and above. Now I will come to some case studies. I'll start with Kanpur power stations, in which we have 22 barrage gates, 17 number barrage bays and 5 under-sluice bays, and 6 head regulator gates. We have Atanapur is at elevation 246.7. In Tanapur power station, sediment management is by flushing through 22 gates, silt excluders provided under sluice bay, and silt ejectors provided in power channel. Till the year 2015, the reservoir lost its capacity to 2.85 mcm from originally 5.96 mcm due to sedimentation in the form of island in the central portion of the reservoir. As you can see here, this is the central portion of the reservoir. A channel through island was constructed by dredging to activate the central flow channel, as a result of which power station has regained the reservoir capacity to 4.05 mcm as per post-monsoon 2018 survey. As per post-monsoon 2019 survey, it is further increased to 4.66 mcm. And now come to Jamera 1 power station, which has largest reservoir of NHPC. It is 540 megawatt project. It was commissioned in 1994. It has 8 spillways at elevation 730 meter and 4 sluices at elevation 670 meter. And FRL is 760 meter, and reservoir length is 15 kilometer on Ravi and 12 kilometer on Stream. As you can see here, the reservoir capacity of Jamera 1 power station and live storage is more or less same since the day of commissioning. And this is L section of the Jamera 1 reservoir for different years, and live storage more or less intact. We lesson learned from Jamera 1 power station, it has large reservoir capacity, and sediment management is by sluicing through low level sluice outlets and following reservoir operation rules, and reservoir level is kept at lower levels in monsoon season, and no sediment related problems has been reported in underwater parts from Chamira 1 power station, which was commissioned about 25 years ago, even though it does not have resilting chambers. The sediment management practice adopted in this project results in a loss of around 0.4% in live capacity per year. Here I would like to mention the world average of loss of capacity, live capacity is around 1%. This is the 5 power station in which we have 3 desilting basins, 5 spillways at low level, that is 540 meter, and reservoir length is 5.1 kilometer, FRR 579 meter. In Tista 5 power station, sediment management is through low level spillway, flushing and sluicing, and then provision of desilting chamber. In spillway glacis, we provided a steel liner now to accommodate, to get rid of erosion. This is reservoir capacity for different years. As you can see, live storage, except for first year, it is more or less at the same level. And this is a section, except this portion, live storage is more or less intact. We did sediment balance through different outlets also. Sediment flushed out during flushings is 37%, sediment passed through SFT 10%, through machines it is 30%, and through spillway, that is sluicing, is 23%. And we learned that for a small reservoir, for reservoir of 13.5 MCM, and the annual sediment load of 12.7 MCS, we were able to maintain the live capacity at 5 to 6 MCM as compared to the initial live capacity of 6.3 MCM. This is the Dhaulaganga power station, which is 280 megawatt project. It was commissioned in 2005 in Uttarakhand. It is CFRD, which is concrete faced backfill dam, and this is spillway portion in which spillway crest level is elevation 1307 meter, and capacity is 2560 cubic at MWL. We have 2 intake that they are at elevation 17.5 meter, and FRL is 1345, MDDL is 1330 meter. In Dhaulaganga power station, we have prescribed this reservoir operation guidelines. I would like to mention for every power station of NHPC, we have prescribed reservoir operation guidelines. In particularly Dhaulaganga power station, we bring down the reservoir from FRL to MDDL between 15th May to 1st June, and during monsoon period, we keep the reservoir near MDDL, that is at 1330 meter. If in case discharge is less than design discharge, 107 cubic in this case, reservoir level will be maintained at slightly higher level. And then after that, we attempt to bring the reservoir level to FRL. Flushing we carry out if sediment concentration at is more than 4,000 ppm and or at 150 cubic inflow or 200 cubic inflow based on the seasons. We also check the efficacy of the silting basin based on observed data. We have found that around 82% of the coarse sediment could be removed from desilting basin. It was also predicted in physical model study. Now it comes to the 2013 flood, that because of that reservoir was filled with RBMs, and you can see here the reservoir tail end. These are the damages caused by sediment during year 2013 flood. This is scoring and erosion below apron area. Erosion in glacis of Dhaulaganga Dam spillway. TRT outlet is completely choked condition. Erosion in pier of Dhaulaganga Dam spillway. In Dhaulaganga, we have provided steel liner in spillway glacis after 2013 flood. This is the reservoir capacity over the years. You can see here that after commissioning, we try to maintain the reservoir capacity close to the original condition. But after, due to heavy flood in 2013, it reduced almost to the half. And we tried to gain the reservoir capacity. But due to insufficient flushing because of the certain reasons, we could not do the flushing, and it reduced to almost by 25%. And again in 2013, we carried out the flushing. It shows and then it is increased. It shows the efficacy of the flushing technique that we have adopted for Dhaulaganga. It is a Chamera 2 power station in which we have provided 4 spillways at elevation 1141 meter and FRL is 1162 meter. And it has 2 desilting chambers and reservoir is maintained at lower level. A reservoir flushing is carried out when sediment concentration increases above 5000 ppm or discharge exceeds 300 cubic. We have 4 flushings, one in each monsoon month. And after 15 years of commissioning of project, live capacity is 1.4 MCM as compared to the original capacity of 1.8 MCM. Reservoir flushing at Chamera 2 power station is carried out in tandem with flushing at Chamera 3 power station, and which is around 24 km upstream of Chamera 2, and it starts the flushing first and give the prior intimation to the Chamera 2 to plan its flushing accordingly. So sediment management project in Cascade is different than that for standalone projects. It is in which cascading effect in reservoir operation for optimization of power generation in lean season and efficient sediment management in monsoon season is considered. We have projects in Cascade in Ravi Basin and in Tista Basin. This is comparison of live storage capacity of different reservoirs of NHPC. You can see from by using different technologies, different techniques as per the project, we are able to maintain the capacity of the reservoirs. With the help of CWPS, we carry out physical model study and mathematical model study to evaluating the and quantification of effectiveness of operational rules for sediment management, and which will help designers to select the location and configuration of outlet works. Recently, as per the physical model study carried out by the CWPRS, in Mangdechu project in Bhutan, it was decided to adopt controlled gate operation and keep reservoir level higher than MDDL for discharge more than 1200 cubic to ensure safety of the structure, which is different than the general philosophy we adopt for the reservoirs of NHPC. So we found these are the best practices to prepare project specific guidelines and detailed standard operating procedures, observe sediment data regularly and accurately and maintain long-term record, conduct bathymetric survey, adopt low-level outlet, operate reservoirs at or near MDDL, ensure free flow flushing, make arrangement for exclusion of sediments larger than particular size, and simulate long-term reservoir sedimentation by mathematical modeling or carry out physical model study, and coordinated and synchronized reservoir operation and sediment management approach for projects in Cascade. This is the conclusion. As we all know, the sediment is threatening the existence of all kind of reservoirs, and Himalayan rivers carry much more sediment load than the capacity available in the reservoirs of power stations located in this region. NHPC Limited has 22 power stations in Himalayan region, successfully in maintaining gross or live capacity of reservoirs satisfactory by low-level outlets and drawdown flushing and sluicing. Desilting basins, silt excluders, silt ejectors have also played their roles, and we have provided project-specific guidelines which are helpful in preserving the reservoir capacity and ensure smooth running of the power station. If proper reservoir operation and flushing guidelines are not adhered to, along with significant loss in reservoir capacity, the machine parts were to be repaired every year. After following proposed guidelines, the repair cycle of the runner and guidelines has increased to 2 to 3 years and 3 to 4 years respectively. Thank you so much for patient hearing.
Thank you, Manjusha, for making such a elaborate and knowledgeable presentation about NHPC powerhouses. It was quite exhaustive and you tried to cover all the aspects. Any questions, please?
Can I have one question?
Yes.
Okay. Yeah, thank you very much. Many interesting topics you are doing in the sediment flushing is especially combining cascade system is almost matching today's my presentation. My question is this kind of you mentioned tandem or cascade. So these coordinating the sediment flushing operation, who decide to start and when this sediment flushing will conduct it. This is scheduled in advance or flat events or like some other. How do you decide the timing?
So actually, the projects that I was mentioning, they are in one that was in Raivivesi, Chamera 2 and Chamera 3 projects. They are both of those projects are with NHPC. So we have carried out exhaustive study to understand how which project will start flushing first. So Chamera 3 that is going to start the flushing first, then it would be the coordinated operation, and then Chamera 2 will do the certain time. So this is because both the projects are with NHPC only, so that's why we could coordinate. Is it the right answer? So is it the what you are?
Yes,
Yeah.
thank you very much. Okay.
I'll supplement what Manjusha told just now. Owner is one for both these projects, and in case owners are different, and then also you have coordination between the upstream and the downstream project. That's the standard practice, and usually during monsoon period, the operators of both these projects they coordinate with each other. Number one. Number two, you asked for how do you decide that when the flushing is to take place.
Yes.
So to that question, you see, like we have very strong forecasting systems these days, and we like have even the real-time decision support system in some of the projects. But based on the rainfall inputs or the intensity of rainfall in these catchments predicted, because we usually get 7 days ahead rainfall prediction based on the Indian satellites and international satellites. Both these are quite elaborate these days. So during monsoon period, when you know that my present discharge in the river is this much, and then in the coming days, I'm going to have so much of rain, then my discharge is likely to be increased beyond the limit of flushing, defined limit of flushing, then we plan for flushing operations. And also, see, like during monsoon, we, as Manjusha told, that they have a standard procedure for flushing of their reservoirs, and NHPC has been flushing out these reservoirs continuously to maintain their live storage capacity. Though they have been increasing, the flushing cost is very high because they have to shut down their power station during that period. So,
okay.
But in that case also they for the flushing, in case we do not do it on monthly basis, in certain other cases, what we do is we have make sure that during the month of end of August or after 15th of August, we carry out flushing whenever we get a chance. Because if we do the flushing in the beginning of the monsoon, then the reservoir gets filled up again with the sediments. So usually it is in the second half of the monsoon. But in NHPC projects, the standard guidelines in some of the projects are that you carry out flushing on monthly basis.
Yeah,
Manjusha, am I?
Yes. On each monsoon months, we have prescribed one flushing. Generally in projects, in some of the projects we have even prescribed it 2 times in a month because of high sediment load or very low reservoir capacity.
Can I have one more question? Is okay?
Yes, please.
Okay. So I understand the operation procedure. So another additional question is this kind of sediment is transported to flushing is downstream, like water quality or high turbidity will pass into the downstream river. Do you have any conditionality how much milligram per liter will be the upper limit, or how many days is it should be keep in the some like a target condition? Is such kind of environmental or some like constraints? Do you have such kind of issues?
Sir, I don't have ready answer for this. Maybe Sir Sharma sir, would you like to supplement on this? Because I don't have a ready answer on this. Maybe if I can get the answer for that.
It's okay. I'll try to answer this question. Professor Sumi, in Indian condition, as Manjusha has already explained, that we carry out this flushing operation during monsoon period. During monsoon period, we already have high discharges in the river even in the downstream portion, because most of these reservoirs which she was talking have only do not have the over the year storage. The reservoirs they are operating have storage which is only for a very limited duration during monsoon period. And during monsoon, the downstream river reach also has sufficient water to carry the sediment load, whatever they flush. But yes, I would agree that there are no such conditions so far on environmental considerations that the sediment concentration has to be this much. So that is how it is.
Yeah, I think yeah, thank you very much. Yeah, also like we have similar condition in the, for example, today I presented the Kurobe River, high sediment concentration is Oka downstream. So at the moment is concentration is not the key constraint. Oxygen, resource oxygen is like a key component for fish life, for example. But maybe monitoring and after recording how to document or to share the downstream stakeholder like fishermen's groups, also environmental authorities and local communities. Those data monitoring and open to the public is like to have a good collaboration with other interest group.
Yes.
Yeah.
In fact, 2 years back, they were coming out with some rules to how to carry out flushing and how much quantum of flushing is to be carried out. But then probably it was resisted by most of the power plant owners in the country on a very basic reason, because they wanted some approvals to be taken before flushing. And the window available for carrying out flushing is very small, because you have to carry out flushing tomorrow. That is how you decide about it. And then you can't write to somebody to give approval or to do that. But your suggestion is welcome step that at least we should monitor these parameters on downstream side. But yes, like it to my mind, it has to be very site specific, because usually in India, we being a big country, they do not have site specific requirements. Most of the time what they do, they make these requirements as a blanket requirement for the entire country, which sometimes is it's good also, because then they can implement it, but then it is not economically feasible, because in many cases you don't really need those requirements are not there. Whatever it is, any requirement for X project is not true for the Y project. So, but so far we don't have any such condition.
Okay, thank you very much. Yeah.
So we move to the next paper in case there are no more questions. Next paper is we will take now by paper by Venkat, Narayan,
Yes, yes,
I
I am
hope
ready,
you are
sir.
ready.
Yes, sir, I am ready, sir.
Excellent. Please proceed.
Sir, good afternoon. Namaste, sir, to everyone. So I am presenting this paper on behalf of S. Narasimha Rao, who is the main author. I am co-author. So we are going to present a case study on sedimentation and sustainable plans and approaches for Nizam Sagar and Sriram Sagar reservoirs in Telangana. So this is the outline of my presentation, sir. Introduction, the problems of sedimentation, siltations in the dams, case study of Nizam Sagar, how the storage loss happened over the years in Nizam Sagar, and various hydrographs are undertaken to assess the situation, and the remodeling works taken to address the situation, and then case study of Sriram Sagar. Then loss of storage and hydrograph service undertaken for Sriram Sagar, and observations in both the cases and conclusions. The sedimentation reservoir generally poses a serious challenge, threatening the useful life of reservoirs in India, sir. Apart from affecting the useful life of storage reservoirs, most of the times it also the functions of the different opportunities of the dam infrastructure. So as this normally happens due to the soil erosion in the catchment area and entrainment of sediments in the water flow and their transportation through gullies, small streams, wagus, and which ultimately joins the main river. So why do we take to study this necessity of study this sedimentation? Because when a project is designed for a certain period, it has to perform its functions, it has to give its intended benefits. So in order to see this situation, to address this situation, we have to frequently carry out hydrograph surveys and assess the situation. Thereby, the economic life of the dam should not be affected. So this is my case study area. This is the Nizam Sagar, which is located on river Manjira, which is a tributary to river Godavari. The second project is Sriram Sagar. This is which is located on main river Godavari at Pochampar. So Nizam Sagar is was constructed Mir Usman Ali Khan, which was taken up in 1923 and completed in 1931. So this was one of the largest dam taken in the pre-independence era. So this was taken up with 29 TMC of water to irrigate 2.75 lakh acres in the area. So it is Mahatma Gandhi and Jawaharlal Nehru also visited this place in 1940. So this dam have a reservoir having a dependable yield of 113 TMC. So basically during the period from 1931 to 1972, this reservoir experienced unprecedented siltations. So these are the design features of Nizam Sagar. Earlier, the canal used to take off at 415 meters and with a silt storage of 2.8 TMC. But during construction, looking at the situation, they have raised the canal silt to 415 meters. So the dead storage at the time of construction was also itself increased to 4.1 TMC. Further, there was provision of scouring sluices, 9 numbers was made at RL 411 to discharge 37,800 cusics. So actually during conceptualizing this project, there was a project called Devanur project was contemplated on the upstream. So when that project was taken up, it will take the siltation which used to flown to this Nizam Sagar will be addressed. So there will not be much reserve. But unfortunately, this project was not taken up. So what happened, sir, in 1956-57, it was observed by that the drawals, daily drawals and depletion were not tallying with the reduction in water stored in the reservoir. It was also noticed that excess depletion in the reservoir is of the order of 15 to 20% at various water levels. So in order to address the situation, to understand the situation, the project authorities first time taken up hydrographic survey in 1967, and the capacity worked out as 14.28 TMC. Against the original capacity of 29 TMC. So there was a loss of about 52% storage was observed. Again, in 1975, another hydrographic survey of the reservoir is also repeated, and the capacity worked out as 12.8 TMC. So the loss of storage from 29 TMC to 12.8 TMC. So there was a total loss of 15.7% the reserve storage due to silting of the reservoir. So in order to address this situation, project authorities thought to undertake some remodeling works. So by virtue of this remodeling works, they proposed to construct a bed regulator, this additional spillway with 20 gates. You can see in that picture. So what happened? It was increased, the FRL was increased by 1.37 meters. So the net increase in the capacity was from 11.74 to 7.8 TMC. So this was one of the remedial measure was undertaken. So further hydrographic surveys were undertaken in 1992 and 2014 using sophisticated integrated bathymetric system. In 2004, even remote satellite imagery were also used. So this is the, you can see the storage capacity at different timelines carried out during different hydrological studies. Actually, original plan in 1930 with FRL 426, the gross capacity was 29.7 TMC. So by providing this remodeling work, besides this additional regulator, the FRL was increased to 428. So present FRL is 428. The previous version FRL is 426. So in 1967, the gross storage was reduced to 14 TMC, and in 1975 survey, it was 12. It was observed at 12.8 TMC. For 1992 hydrographic survey with present FRL, that is increased FRL, the loss of storage was observed as 17.54 TMC. With present, again in bathymetric survey, which was done including satellite imagery, integrated satellite images, the with present FRL, the storage was increased comparatively, loss of storage was reduced a bit. So if you observe this rate of siltation, which was 6.37 per 6.37 hectare meter per 100 square kilometer area, were reduced to 4.49 with the present FRL in 2004 bathymetric survey. So the total capacity, if we assess, is reduced by 38%. So whereas, but by virtue of this, by providing this additional spillway, increasing FRL, we could able to increase storage by 20%. So some of the observations in this one is there was a repeated hydrographic survey was helped to assess the situation, and then the remodeling works were undertaken. So that since remodeling works carried out, there was a declining trend in the silt deposition. This is mainly due to factors also like coming up of project in the upstream area in Maharashtra, Karanja project and Tirna in Maharashtra, and there is a barrage at one Singur Dam at 130 kilometers and another Manjira barrage at 8 kilometers. Besides this, number of irrigation projects were also undertaken in the, on the tributaries and as well as the main tributaries, small medium irrigation projects also. So this was addressed the total rate of silt situation in the Nizam Sagar project. So coming back to this second case study, sir, Sriram Sagar project. This project was taken up on river Godavari. This is, you can see the picture. This project is to serve 9.68 lakh acres in the northern Telangana region. It was constructed with a gross storage of 112 TMC in 1970. The first water was let out in 1963. This was inaugurated by Pandit Jawaharlal Nehru. So a provision of dead storage of 30 TMC was made in the planning stage, assuming the reservoir life of the reservoir as 100 years. So CWC recommended that for this catchment, the rate, silted deposition would be at the rate of 1.2 acres feet per square mile per year. So to address the situation, it was observed that there is a loss in storage, and then to understand the situation, hydrograph surveys were carried out in 1984 and again in 1994. Further hydrographs are also carried out using sophisticated bathymetric system in 2006 and in 2013 as well. So the survey results are you can see in the next slide. As per 1970, plant storage, gross storage 112 TMC. This 1994 study hydrographic survey, it was reduced to 90.31 TMC, and APRL bathymetric survey again shown the reduction to 79.9 TMC. However, the integrated bathymetric survey done in 2004 shown storage as 80 TMC. So if you look at the annual percentage of loss, for 1994 it was 0.81%, in 2006 0.79, and 2014 is 0.647. So the total loss in capacity comes to around 31.90, say 32 TMC, which works out to 28.49 TMC. Whereas the CWC recommended is 1.2 acre feet per square mile. So within the this rate of siltation is within the limit. But how we could achieve this? So the annual percentage of loss in reservoir storage is reduced over period time is only 0.81 to 0.647. So this is due to adoption of several remedial measures taken to arrest siltation with an amount of about 20 crores, which is about 0.5% of the cost of the project, include for the dam component. Like 150 number of construction of silt arresting tanks in the catchment, construction of check dams on the streams joining the river, and afforestation in foreshore area. So definitely, looking at this situation of Sriram Sagar, we definitely recommend that to avoid the sedimentation, there should be a definite some percentage should be of estimated cost should be maybe spent on operational cost for every years as a remedial measures. So we can conclude looking at these two experiences, sir. So the rate of sedimentation observed in case of Sriram Sagar provides importance of monitoring, sir. We could able to assess the situation with periodic hydrographic survey only helped in assessing the situation. The observation of silt and sediment load in streams, big or small, should be made regularly to save the future loss in the utilization capacity of the reservoirs. Then, sir, additional bed regulators in the bund alignment, which was provided in case of Nizam Sagar project, will help in flushing out the soil depositions in the foreshore, and also which helped in increasing the FRL and overall storage. This kind of arrangement also we can think of. Then we can also think of measurement of sedimentation by mathematical models needs to develop for major projects with related to storage. So periodic surveys of reservoirs may be undertaken to assess the rate of sedimentation reservoirs with a separate wing having exclusive central financial asset. There should be assistance, sir. We look at dam rehabilitation, but we don't look at the investment during this process. So there should be exclusive fund also towards the sedimentation assess reservoirs in the CWC level, sir. Thank you very much, sir. This is complete my answer.
Thank you, Mr. Venkata, for good presentation. Any questions, please? Okay, if there are no questions, then let me make a Ankita, I would request you to please mute your microphone. There's a lot of background noise.
Okay, sir. Okay.
Mr. Anuj Kamal also.
Yeah.
If you can mute, your microphone, it would be nice.
Mr. Venkat, can you just mute your mic?
Yeah. 1 minute.
Mr. Sharma, you're mute. Please unmute yourself.
Sorry. Sorry. I have a small comment to make on presentation by Mr. Bankat. Mr. Bankat,
Yes, sir.
you carried out last time the mathematics surveys in the year 2014. Then you suggested there should be some fund available in Central Water Commission for carrying out such surveys. I would say to you, it's a very simple thing. It's not a very complicated thing to do. Please buy the machine carrying out this mathematical survey. Equipment is not very expensive. Buy it once, maintain it properly, make young engineers use it. The survey can be done in a couple of days or about a month. So you should at least carry out these surveys manually so that you are aware what is happening and you should be able to take your remedial measures accordingly.
Okay, sir. Thank you. Noted.
Yeah, it's not, you see, like I would say, everybody who is maintaining these reservoirs should have this equipment, enough equipment, and should carry out surveys regular interval.
Okay, sir. Thank you.
Let's see. It's an example on. I have a question here in chat box. Example on desilting Pilar Dam, 10-meter high in Tamil Nadu, and ends at Bhavani Sagar Dam, who will have extreme loss of storage capacity. Okay, I think this is just a statement, not a question. So with that, if there are no further questions, let me move to the next paper, addressing sediment-induced problems under dam rehabilitation and improvement project in India, Sanjay Giri. Mr. Giri, is he there?
No, I think he's not here.
Okay, so if Mr. Giri is not there, then we can request sedimentation of reservoirs in India by Mr. Anuj Kamal.
Yeah, I am Anuj Kamal. Good afternoon to all of the members present here. And probably I am the last speaker for this Icold conference. So I take that credit. And no, my presentation, let me just share my screen. Is my screen coming?
Yes.
Yes.
Anuj, we can see.
Okay, so my presentation is basically on the holistic view of sedimentation of reservoirs in India. And this we know is the loss of is an invisible source of water which is now available with us as our reservoirs are getting silted. So this desilting the reservoirs can be another source of water. So based on that and based on the paradigm that now we have to work for the basin wise studies of the system, because now river basin hydrosedimentology has become a very important aspect. Unlike the earlier aspects when we used to take our design rates of sedimentation on geographical area basis, we need to concentrate more on basin hydrosedimentology and collection of data based on sediments that move hydrodynamically through a river in a basin. We know that the basin is affected by the human activities, which is the main source of sediment movement, the sediment tapping, erosion of hydrology, and rainfall and other degradation. All this happen in a closed domain of basins. So we have to have a database based on basins, and we try to do it in our Central Water Commission. We generally collect the data on various states, and then we try to assemble them in basin wise. Here we are seeing that this is a Morocco case, a small example that the river is carrying sediments from high erosion area and the lower localized erosion areas, and the sum total of that is actually happening. And river acts as a carrier for sediments, and all the sediments get deposited in the reservoirs. So we have to work on that basin-wise studies. And looking at the basins of India, as per Central Water Commission, we have classified them into around 20 basins with basin codes. There are different varieties of different characteristics of basins in India. The northern basins are more unconsolidated and younger, and the southern basins are more old and more balanced in terms of sediment load. The human activity, impact of human activity on basins, we try to compile on 40 years growth of population during the basin states, and we found that the major basins where the human population was increased during last 40 years was this northeastern India and the western part of India. Some of the few basins which are deeply affected was the basin number 14, which is west flowing rivers of Kutch and Kathiawar. Now, sedimentation data which is available in Central Water Commission is in numbers. We have got around 4,600 reservoirs in India, for which data for sediment data for around 370 was compiled by us, which is generally around 8%. Though in India there are around 5,700 dams, but we have more or less compiled data for 4,600 dams. And in terms of storages, we have around 257 BCM storage in India, and out of that 204 BCM storage data is available in Central Water Commission, and out of that 142 BCM storages data for sediments is available. Now this Icold studied the sedimentation rates in global reservoirs, and based on that they found a global average of 0.72 in 2009 study. And fortunately, when we tried to assemble the data on our basin-wise studies, we arrived at the same rate, more or less of the same rate. So we found that the basins which have built up storages had a more aggravating rate of loss of storages. The live storage data is still being compiled in Central Water Commission because that is still to be collected more aggressively from the dam owners. Based on these studies, which is all available in my paper, we just come to the conclusion part that there were many reservoirs where the design rate of siltation has been surpassed. Now, in 18 such cases, the design rate has been surpassed by more than 5 times. Now, this is a very alarming situation because when I design a dam or reservoir, I take a certain parameter as a design rate, and when it is not matches with the actual rate, then we have to look into the areas of modifying that aspect. Coming to the basin wise, the reservoirs for which we had design rates and for which we had the observed rates, we just try to compare that in Ganga basin for 13 reservoirs, the factor was 2.3. I mean, this is another aspect which for Ganga, for Krishna, and for Tapi also, and for Mahanadi, we observed that the design rate was surpassed and it was deviated much more. For 260 reservoirs data, we found that the loss of percentage was more in 52%, for more than 1%, and for 65%, it is between 0.5 to 1% in gross storages. For 257 reservoirs, in percentage loss of capacity of reservoir, we find that percentage loss was more in 67%. And similarly for it, for yeah, and we know that the effects of reservoir sedimentation is enormous on our loss of storages and loss of navigable depths and abrasion of the turbines. We have been seeing this throughout our Icold conference. But the major part is that it also have burden of removal of the trapped sediment, and it also is a loss of storage. So we observed that around 1.5 BCM loss we lose every year, and that is around $1,600 million of creating for a new storage. This is a huge economic aspect of sedimentation. We have to, if we see it holistically for all over the basins. Now, shrinking net storages is another source of invisible water, and we have to work it out that we can design it sustainably so that we can recover these storages. There have been many sedimentation management options available with us. For example, for upstream management, for sediment routing we have, and for sediment removal. The three aspects are available for upstream and downstream management, and we have to make an option of going ahead with the best one. The sediment modeling has been discussed in this session also, that we have to work on a cascade system for flow and morphological studies for a basin wise, and to understand the design rates and to understand the sedimentation rates. Now, to conclude is that our analysis is generally based on around 8% of the number of storage dams in India, and which we hope to increase and update as early as possible in a mission mode. The basin hydro sediment studies need to be the basis of reservoir sedimentation, which is not happening as of now. We are still basing our estimates on some thumb rule basis on a geographical area, and we have to polish that technique to include sedimentation modeling of reservoirs and to include the cascade river reservoirs system to arrive at the design rate of sedimentation. Then the unique each reservoir system is unique. We have to have a upstream downstream balancing system for dam raising, sediment management plan, and regional sedimentation and its environmental impact. We have to see that we in India we have got large reservoirs which have crossed the age of 25 years, so they are more aging and more sedimentation. We don't have data in India for small dams for which the rate of sedimentation is higher than the large reservoirs which have lesser sedimentation rates. And we have also identified some of the some of the basins which we could identify as, for example, basin code number 14 has been identified as the most critical to reach because it has got around 483 dams and it is getting sedimented very fast. So with this, I think more insight will be taken up by more deeper study with us and by other organizations. Thank you.
Mr. Anuj, thank you for your presentation. It was really good. Any questions, please?
Thank you very much. Okay. Thank you very much. Very interesting topics. It's Central Water Commission, right?
Yes. Yes.
So you are the very important key person to collecting all Indian data, right?
Yes. 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 Yes.
Okay, very interesting. So my question is, how did you select 8% of dams, target dams?
No, there is no criteria for selecting. We are in a process to collect data for all 4,600 dams, for which we have got other data, hydraulic and hydrological data available with us. Unfortunately, sedimentation data is not available. There is no fixed rule. I mean, those 370 are those for which we could get the information at the first hand. And we are in a process to collect more information. That has been taken up now aggressively in National Hydrologic Project also. And we hopefully have to do it in another 3-4 years to collect the data for all dams in India.
Okay. So next question is such kind of bathymetric survey. Do you have a kind of like a guideline or soft guideline? How often are you recommended to measure?
Yeah, we as a director of sedimentation in Central Water Commission, I framed the guidelines for the hydrographic surveys for the reservoirs using robotic boats, and we hopefully have tendered for that, and we have tendered for around 100 reservoirs using those techniques, and these guidelines are available. I can share with all concerned or with Icold in case somebody wants. These guidelines have been upgraded. We have upgraded the guidelines of Icold. Icold issued guidelines in around 75, and we just upgraded this with the latest technologies, taking the latest which is available in the market. Based on that, we have, and there's a robotic boards, as Dr. Sharma has also indicated, that can be done by any dam owner or authority. But for other authorities, for other states and other organizations, we have provided financial assistance also, and under National Hydrological Project, we are now doing surveys for around 100 reservoirs at present.
But based on your experience or like knowledge, how often, average, how often they are doing?
No, you see, yes, that's a very good question. You see, we have to do it every 10 years to have a
10 years.
Yes, to have a realistic assessment of where the things are moving. But unfortunately, we have data only for one time. For most of the reservoirs, we have only one time mathematical data. So that is, and that is also quite old. For example, around 20% of the reservoirs data must be around 1990s, so it's 20 years old. I mean, that's still need to be updated. So that is another thing which need to be done in a routine manner, and a standard SOPs has to be issued to the dam authorities to undertake it in a routine manner.
Professor Sumi.
Yes.
I have to add something what Mr. Anuj mentioned. See, what is happening at the moment is that these dam authorities are acting at their own. But in certain cases when big dams are there, the surveys, the time interval at which surveys are being conducted is different by different authorities. But in certain cases, like for instance, the dams which I was looking after, we used to carry it biannually. publish these reports on biannual basis and used to understand what is happening to our reservoirs. So the good idea is to, I would say that for bigger reservoirs, we can't say that each and every reservoir should carry it out biannually. But for instance, NHPC reservoirs, the Manjusha made a presentation where she showed that they carry out every year. So basically, depending on the size of the reservoir and importance of these reservoirs, I think we need to be conducting these surveys. But if not annually, biannual is a good time period. We should be doing it.
Yeah, I just want to add that reservoirs which are 25 years or more in age and which are in storage, not a run of a river type system, they can be done in 10 years, 5 years or 10 years interval, and that gives a reliable picture for their loss of storages.
Manoj, though it's okay what you are saying, but see, like reservoirs which are very old, the 1960 reservoirs, all the three reservoirs I'm talking to you were constructed in the year 1960, 1966, and then 1977, and the surveys are being carried out biannually. There's no reason to carry out the surveys in 10 years because by that time you take the corrective actions, it would be too late. We need to be understanding the sediment behavior of these reservoirs on regular basis and carrying out the remedial measures in the catchment upstream. If we have to maintain the life storage of these reservoirs.
Yeah, I agree. I do agree with you.
Yes, I also agree, sir, because I showed it in Dholiganga's slide as because of less number of flushing, we lost the capacity, so we had to take corrective actions to increase the capacity. So if we did not have survey, we could not have taken any action.
Okay, very good, Manjusha. Thank you.
Thank you very much.
I have one question to Anuj. Anuj, can you please throw a little light? What would be the gross storage, the available live storage available in all the reservoirs across India? Just how much is the total sedimentation which would have occurred in the reservoirs in India?
Yes. We had a data for around 86 reservoirs for live storages, and it is given in my paper. I'll just go through it and I'll give you, because we computed on the gross storage, because now getting differentiating between gross and live storage is now very difficult.
Just a second. No, just a second. I'll reframe the question. If you can please tell what is the gross storage available in the reservoirs across India? You gave some figures that
257 BCM. 257 BCM.
257 is the storage available at the time of construction. What is the available after sedimentation?
You want a sedimented?
Yeah, after sediment. See, like there's no question of talking, and I think this is a very false illusion which we are talking in this country that it is 257. No, I think that's a very not the correct thing. What is after sedimentation? What is the exact number? Can you please?
Yeah, we have
some
compiled.
light.
No, I think I am not having the data right in the ready format right now, but it is available in my paper. I've submitted to Icold for various basins, and that has been taken from the number of reservoirs from the state figure. So I have not compiled that data, but I think I have indicated somewhere the gross storage is also, because for 204 for 204, let me just go through it.
It's okay. I think if it is given in your paper.
Yeah. It is given in my paper. It is given in my paper. Yes.
Thank you.
Right.
If there are no more questions, we have I got a message from the virtual host that we have a recorded presentation from Mr. Sanjay Giri. So let's I request the virtual host to kindly play that recorded presentation of Sanjay Giri. It is addressing sediment-induced problems under the Dam Rehabilitation and Improvement Project in India. No audio, please. There's no audio, please. Virtual host, please see to this problem.
Sir, there's no audio in this video.
Okay, so we can, if there's no audio, then I don't think the audience can understand anything out of it. So we'll skip this presentation. You can please stop this presentation. Okay, so I think we have come to the end of this workshop. We have had 12 papers presented by different authors. It has been a very knowledgeable and very nice presentation by everybody. And I think especially the Indian delegates who have been facing this problem of sedimentation in their different dams throughout the country would get benefited by the experience and discussions with the international experts from Malti Teal from US, then Professor Sumi from Japan, Nicholas from Spain, then we had Hans Engrubs from, I think he was from Denmark. Then we had other speakers from Japan, Mr. Acharya from Nepal. So it was a very good learning experience and sharing of our knowledge with each other. And I must thank especially the Malti-Tail, Professor Sumo, Dr. Nicholas, Hans Engrub, who very readily, in the very beginning when we conceived this workshop, they very readily agreed and came forward to be presenting their experiences in the workshop. And then it was supplemented by our other friends from Japan and then from Indian authors who made excellent presentation. Mr. Dheeraj Acharya from Nepal also gave a very good overview of the dam which is under planning in Nepal. So in the end, I have to say a big thank you to everybody for being part of this workshop and sharing the knowledge. Thank you very much. In case somebody has to add, I would request to please come forward and give their viewpoint. Anybody who want to make a comment?
Yeah, thank you very much. Very nice discussion. Yeah, I'm very happy to have an interesting discussion. Thank you very much.
Thank you so much, sir. Thank you, everyone.
Thank you very much.
Okay.
Thanks.
Thank you very much.
Thanks
Very interesting and very nice presentations and discussions. So really excellent workshop.
Thank you, Nicholas. Thank you so much. So we close it now. Thank you, everybody, once again.
Okay,
I'm
bye.
closing the meeting. Bye-bye.
Okay.